Look up at the night sky on a clear evening, and you'll see a breathtaking tapestry of stars, planets, and the faint, glowing band of our own Milky Way. It's a view that has inspired humanity for millennia. But what if everything we can observe, every galaxy, every nebula, every shimmering point of light, is only a tiny fraction of the full picture? What if the universe we think we know is built upon a foundation of hidden structures, an invisible architecture that dictates the shape of everything from the largest cosmic web to the smallest particles? This isn't science fiction, it's one of the most profound frontiers of modern cosmology. For generations, we've mapped the heavens, believing that if we could just see far enough or look closely enough, we would uncover all of reality's secrets. Yet, the deeper we peer into the cosmos, the more we realize that the true nature of the universe might be written in a language we are only beginning to decipher, etched into frameworks we cannot directly see. These are the hidden structures of the universe, the underlying principles and formations that might act as the invisible scaffolding of reality itself. Think of it like this: when you look at a magnificent building, you admire its facade, its windows, its design. But holding it all up, hidden within the walls, is a framework of beams and supports the essential blueprint that gives the structure its form and stability. In the same way, cosmologists now theorize that our universe could be shaped and governed by extraordinary constructs operating behind the scenes. From cosmic strings, fabric of space-time defects thinner than an atom yet stretching across the entire cosmos, to the mind-bending possibility that our three-dimensional reality is merely a holographic projection from a distant two-dimensional surface, these ideas challenge our most basic perceptions of existence. They suggest that what we perceive as empty space, the forces of gravity, and the very flow of time could all be emergent properties arising from something much deeper and far more strange. In this video, we're going to explore 30 of the most incredible theories about these hidden cosmic structures. This will be a journey through the wildest and most profound ideas in physics, a tour of concepts that sound like they're straight out of a fantasy novel, yet are taken seriously by brilliant minds around the world. We'll dive into theories proposing extra dimensions curled up impossibly small, examine the cosmic lattice that may guide the formation of galaxies, and even question whether our entire universe is just one bubble in an endless, frothing multiverse. This isn't just about presenting a list of facts, it's an invitation to stretch your imagination, to look at the night sky with new eyes and wonder what incredible secrets are still waiting to be uncovered. The journey into the universe's hidden layers is just beginning, and the discoveries we make there could fundamentally change our understanding of reality itself. Are you ready to explore the blueprint of the cosmos? Our journey into the hidden architecture of the cosmos begins with one of the most fascinating and elusive proposals: cosmic strings. Imagine, if you will, the universe in its very first moments, a seething, hot, an incredibly dense soup of energy and fundamental forces. As the newborn cosmos expanded and cooled in that fraction of a second after the Big Bang, physicists believe it underwent a series of profound phase transitions, much like steam condensing into water or water freezing into ice. And just as freezing water can trap bubbles or cracks as it solidifies, the fabric of space-time itself may have frozen with imperfections, incredibly thin floor lines in reality. These are the cosmic strings. They are not strings made of any material you know. They are thought to be fundamental flaws, one-dimensional cracks in the very structure of the universe, thinner than a proton yet so massive that a single inch of one could weigh more than a mountain range. Their existence is a direct prediction of several grand unified theories, which attempt to merge the fundamental forces of nature, and if they are real, they would form a network of unimaginable scale, stretching across the entire observable universe, longer than galaxies and potentially looping back on themselves in colossal, vibrating rings. The influence of such an object would be profound. A cosmic string's immense density creates a gravitational field unlike any planet or star. It wouldn't just pull matter towards it, it would warp the space-time around it in a unique way. Because it is a one-dimensional defect, the geometry of its gravitational pull is razor-sharp. Picture a perfectly straight cosmic string slicing through the void. Space around it would be distorted, not like a bowl-shaped depression, but more like a missing wedge. If you were to travel in a complete circle around the string, you would find that you've returned to your starting point having traversed less than 360 degrees. This bizarre warping would have a startlingly observable effect: gravitational lensing. Light from a galaxy directly behind a cosmic string would be forced to travel along two different paths around this cosmic fault line, creating not one, but two identical mirror image copies of the same galaxy in our telescopes. Astronomers actively search the skies for these telltale double images, a potential signature of these invisible scars from the birth of the universe. While definitive proof of cosmic strings remains elusive, their potential discovery would be a monumental breakthrough, providing a direct window into the universe's most violent and energetic first moments, and confirming that the fabric of reality itself bears the marks of its own dramatic creation. Moving from the cosmic strings that could stitch the fabric of space-time to another mind-warping concept, we encounter a theory that challenges the very nature of dimensionality itself, the holographic principle. This idea proposes a radical notion that our universe, with all its rich depth, its soaring galaxies, and the very space you occupy, might not be fundamentally three-dimensional at all. Instead, what we experience as a three-dimensional reality could be a projection, a holographic illusion encoded on a distant, two-dimensional surface that surrounds us. Think of the shimmering, three-dimensional image you see on your credit card. It appears to have depth and volume, yet all that information is stored flatly on the metallic strip. In a similar, though vastly more complex way, the holographic principle suggests that our entire cosmos might be a cosmic hologram, with all the information describing every star, every planet, and every one of us actually existing on a remote boundary, a two-dimensional shell at the edge of everything. The seeds for this astonishing idea were planted not in the study of holograms, but in the enigmatic physics of black holes. In the 1970s, physicist Jacob Bekenstein made a revolutionary discovery. He found that the maximum amount of information, or entropy, a black hole can contain is not proportional to its volume, as you might intuitively expect, but to the area of its event horizon, the spherical surface from which nothing, not even light, can escape. This was a profound clue. It implied that all the information about everything that ever fell into a black hole, every atom, every history, every detail, could be entirely encoded on its two-dimensional surface. Later, building on this, other scientists like Leonard Susskind and Gerard T. Hooft proposed that this might not be a special property of black holes, but a fundamental feature of the universe. If a region of space can be completely described by information on its boundary, then perhaps our entire observable universe is just such a region, with its boundary being the farthest, oldest surface of the cosmos we can possibly see. The implications of this are staggering. If the holographic principle is correct, then reality is not fundamentally made of the three-dimensional objects we perceive, but is instead built from information. What we experience as depth, volume, and the continuous fabric of space is an emergent property, an incredibly convincing illusion generated from a vast, complex calculation happening on a distant, flat screen. A helpful analogy is a modern, immersive video game. The world you explore on your screen appears to be a vast, three-dimensional landscape, but every mountain, every character, and every physical law is actually generated from a two-dimensional set of codes and algorithms on your computer's hardware. In the cosmic version, the universe is the rendered game, and the two-dimensional boundary is the cosmic hard drive where the fundamental code of reality is stored. This perspective forces us to reconsider the very nature of existence, suggesting that at the most basic level, the universe might not be made of stuff, but of bits, the fundamental units of information, projected into the rich, three-dimensional reality we call home. But if the idea of our universe being a projection wasn't enough to stretch your mind, prepare for a concept that expands the stage of reality to an almost unimaginable scale: the Level 1 multiverse. This isn't about traveling to a parallel Earth through a magic portal. This is a theory grounded directly in the physics of the Big Bang and the phenomenon known as cosmic inflation. The core idea is deceptively simple. If the space of our universe is truly infinite, or at least immeasurably vast beyond what we can ever see, then every single physically possible event must happen. Somewhere out there, far beyond the reach of our most powerful telescopes, there exists a region of space where everything is identical to our own cosmic patch. A region where another you is reading this very sentence on an identical Earth, orbiting an identical sun, and that's just the beginning. This staggering conclusion comes from a marriage of two powerful ideas. The first is the theory of eternal inflation, which describes the frenzied expansion of the universe in its first moments. Picture the newborn cosmos not as a single, smooth explosion, but as a pot of water coming to a boil. The entire universe was filled with a strange, high-energy field that caused space to expand at an exponential, unimaginable rate. But like a boiling pot, this expansion wasn't perfectly uniform. In most regions, this inflationary field decayed, its energy converting into the hot soup of particles that would become our galaxies. But in other regions, the field persisted, causing those pockets of space to keep inflating at a fantastic speed. Our entire observable universe, all 93 billion light-years of it, is just one single bubble that stopped inflating in this vast, ever-expanding cosmic foam. An infinite number of other such bubbles exist, each a separate universe within a greater multiverse. The second key idea is the nature of infinity itself. In our observable universe, there are a finite number of ways particles can arrange themselves. It's a number so large it's practically meaningless to us, but it is finite. Now, if the wider space beyond our horizon is infinite, and it contains a finite number of possible particle configurations, then repetition becomes not just likely, but mathematically inevitable. Think of it like shuffling a deck of cards. With a standard deck, there are a vast number of possible sequences, but if you shuffle that deck an infinite number of times, every single sequence, no matter how unlikely, will appear again and again. In the infinite cosmic landscape, the same rules apply. There will be regions where the particle arrangement perfectly matches our own, creating a volume of space indistinguishable from ours. There will be others where just one atom is out of place, and still others where history unfolded with dramatic differences, where the Earth never formed, or where life took a completely different evolutionary path. What does this mean for our own cosmic story? It suggests that our universe, which feels so unique and special to us, might be just one ordinary member in an infinite ensemble. The conditions we see, the specific strength of gravity, the mass of the electron, the number of spatial dimensions might not be the result of a single, finely tuned cosmic lottery win. Instead, they could simply be the local bylaws of our particular bubble. In an infinite multiverse, every possible set of physical constants and initial conditions is realized somewhere. We find ourselves in this particular bubble not because it's the only one, but because it's one of the rare ones that allowed for galaxies, stars, planets, and ultimately, life to form. This concept doesn't diminish our existence, it reframes it, placing our local reality within a context of such immense grandeur that the cosmos becomes less of a single creation and more of an endless, dynamic tapestry of possibilities. While the Level 1 multiverse presents a cosmos of infinite repetition, the theory of Level 2 takes this strangeness to an entirely new dimension of diversity. Here we venture into the realm of bubble universes, a concept born from the most successful theory in modern cosmology, inflation. But this isn't the simple one-and-done inflation that gave our universe its initial push. This is the theory of eternal inflation, a process that never truly stops, generating an endless sea of cosmic islands, each with its own fundamental rules. Picture that same pot of water boiling, but now imagine it's a cosmic pot of infinite size. The water represents an unstable, high-energy field called the inflaton field. As this field boils, most regions rapidly lose energy, cooling down and transitioning into the stable, low-energy state that allows for the formation of particles, galaxies, and us. Each of these calm regions is a bubble universe, but here is the crucial twist. The process of inflation itself creates more space, and it does so exponentially faster than the bubbles can form and merge. So, while our entire observable universe is the interior of one single bubble that stopped inflating over 13 billion years ago, the space between bubbles continues to inflate at an unimaginable rate, forever pushing these cosmic islands apart. The greater structure, the eternally inflating meta-universe, becomes a foaming, chaotic ocean, with new bubble universes constantly nucleating within it, each one completely isolated from all the others by an ever-widening gulf of hyper-expanding space. They are not connected in any way we can conceive. They are separate realities born from the same cosmic process. Within this framework, the diversity of these bubble universes is not just about different arrangements of particles, as in the Level 1 multiverse. In the Level 2 scenario, the very laws of physics can be different inside each bubble. When a region of space undergoes its phase transition and drops to a lower energy state, it's like water freezing into ice. But the way it freezes can lock in different properties. The strength of gravity, the mass of an electron, the number of fundamental forces, and even the number of spatial dimensions could be set randomly during this process. Our universe has 3 dimensions of space and 1 of time, with gravity being remarkably weak. But there could be bubbles out there with 4 spatial dimensions where gravity is the dominant force, and the structures within are shapes we cannot possibly visualize. Other bubbles might have a stronger nuclear force, causing all their hydrogen to fuse into helium instantly after the Big Bang, leaving no fuel for stars to ever form. These are not just different histories, they are entirely different realities built on different physical frameworks. This provides a compelling, if humbling, answer to one of the greatest mysteries in physics. Why is our universe so perfectly tuned for life? The constants of nature seem exquisitely fine-tuned. If gravity were just slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang. If the force binding atomic nuclei were just a bit weaker, no complex elements would ever form. In the context of a single universe, this seems like an incredible coincidence. But in the Level 2 multiverse, it's no coincidence at all. With an infinite number of bubbles forming across an eternal landscape, every possible combination of physical constants and laws will be realized in some of them. We, quite obviously, can only exist in one of the rare bubbles where the constants allow for the formation of stars, planets, and carbon-based life. We don't live in a special universe, we live in a habitable one. Our local laws of physics are not a fundamental decree for all of existence. They are merely the local bylaws of our particular cosmic neighborhood, a fortunate accident in an unimaginably vast and varied cosmic metropolis. Now we shift our perspective from the vast cosmic landscape to the strange and uncertain world of the quantum. If the Level 2 multiverse is a sea of separate bubbles, each with different physical laws, then the next theory proposes a multiverse of an entirely different kind, one that branches off from our own reality with every fleeting moment. This is the many worlds interpretation of quantum mechanics, a concept that suggests the hidden structure of the universe isn't made of strings or holograms, but is a constantly dividing, ever-branching tree of parallel realities, all equally real. To understand this, we first need to grasp a fundamental oddity of the quantum realm. At the level of atoms and particles, the world does not behave in the definite, predictable way we are used to. An electron is not simply in one place or another. It exists in a blur of all possible positions, a state known as a superposition. It's only when we measure it, when we observe it, that this cloud of possibilities seems to collapse into a single, definite outcome. For decades, the prevailing explanation was the Copenhagen interpretation, which essentially said that the act of observation forces the quantum system to choose one reality. But this always left a troubling question. What or who exactly counts as an observer? Is it a conscious human, a cat in a box, a machine? The many worlds interpretation proposed by physicist Hugh Everett in the 1950s offers a breathtakingly elegant and radical solution. Nothing ever collapses. Everett's theory states that every time a quantum system faces a choice, every time an electron could be spun up or down, every time a radioactive atom could decay or not decay, the universe does not make a single selection. Instead, it splits. The entire cosmos fragments into multiple branches, with each possible outcome realized in a new, parallel world. In one branch, the electron is spinning up. In another, newly created branch, it is spinning down, and both of these branches are completely real. This branching isn't a rare event, it's happening constantly, an incalculable number of times every second for every quantum particle in existence. The result is a mind-bogglingly vast multiverse, a tapestry of near-identical realities that diverge with every quantum decision, creating a structure of parallel histories and futures that is beyond astronomical in scale. This leads to profound implications for our own sense of self and the nature of free will. In the many worlds picture, there is no single you. There is a version of you reading this sentence in this branch of reality. But at this very moment, quantum events in your body, in the air around you, in the device you're using, are causing the universe to split. In one branch, you decide to get a glass of water after this video. In another, perfectly real branch, you do not. There is a branch where a cosmic ray missed a crucial strand of your DNA a moment ago, and another branch where it did not. Every possible version of your life, every decision you could have made, and every random accident that could have befallen you is playing out in some branch of this cosmic tree. Your consciousness, from your perspective, seems to follow a single, linear path, but that is only because you are experiencing one thread in an infinite tapestry. Your other selves are experiencing their own threads, all of them valid, all of them real. So if all these worlds are real, where are they? The hidden structure of the many worlds multiverse is not a spatial one, like bubbles floating in a higher dimensional space. Instead, these parallel realities are right here, superimposed on top of one another in an abstract, high-dimensional state space called the universal wave function. They are separated not by distance, but by their quantum decoherence, meaning they have simply phased out of contact with one another, like different radio stations broadcasting on different frequencies. We are forever trapped within our own branch, unable to perceive or interact with the others. This interpretation removes the mysterious role of the observer and paints a picture of a deterministic yet endlessly branching cosmos. While it solves some of the deepest puzzles in quantum theory, it forces us to accept that our reality is just one page in a book of endless possibilities, a single narrative in a library that contains every story that could ever be written. From the endlessly branching worlds of the quantum multiverse, we now journey to a theory that reimagines the very origin of our cosmos, proposing that our universe was not born from a singular point of infinite density, but from a spectacular collision between two vast parallel realities. This is the ekpyrotic universe, a concept born from the framework of string theory and brain cosmology. In this model, our familiar three-dimensional universe is not all there is. Instead, it is a three-dimensional brain, a word short for membrane. Think of a brain as an immense flat sheet, a vast floating plane of existence. Our entire cosmos, with all its galaxies, stars, and planets, is confined to this single, three-dimensional sheet. But this brain does not float in nothingness. It exists within a higher dimensional space known as the bulk. Within this bulk, there could be other brains, other parallel universes, floating like gigantic, invisible pages in a cosmic book. The ekpyrotic scenario offers a dramatic alternative to the traditional Big Bang. Instead of a hot, dense singularity, our universe's beginning is envisioned as a collision. Picture two of these immense parallel brains floating in the bulk. They are drawn toward each other, moving slowly through the higher dimensional space. When they finally meet, they don't crash and shatter in a destructive sense. Instead, they collide and bounce apart. From our perspective, trapped within one of these brains, that moment of collision would appear as an enormous release of energy, flooding our brain with heat and matter, and initiating a period of rapid expansion. This event, which we perceive as the Big Bang, was not the absolute beginning of time and space, but a phase transition, a cosmic reboot triggered by an encounter with a neighboring reality. This model elegantly addresses one of the great puzzles of the standard Big Bang theory. Why is the universe so uniform? The traditional model requires a brief period of inflation to smooth everything out, but the ekpyrotic model provides a natural explanation. Before the collision, the two brains could have been interacting and settling into a uniform state over an immensely long period. When they collided, that uniformity was imprinted onto our newborn universe, explaining why the cosmic microwave background radiation appears so even across the sky. This brain world picture also opens the door to a profound explanation for one of the most fundamental mysteries in physics, the surprising weakness of gravity. Why is gravity so many orders of magnitude weaker than the other fundamental forces, like electromagnetism? In the brain cosmology model, the answer might be that gravity is not confined to our brain. While all the particles that make up matter and light, electrons, quarks, photons, are stuck to the surface of our three-dimensional sheet, the graviton, the hypothetical particle that carries the gravitational force, could be unique. It might be able to leak away from our brain and propagate through the higher dimensional bulk. From our point of view, this leakage would make gravity seem diluted, its influence stretched thin across the extra dimensions. It's as if we are living on the surface of a pond, and we can only perceive the ripples that travel along that surface, while the true depth and full motion of the water extends far below into dimensions we cannot directly access. This single idea could transform our understanding of the cosmos, suggesting that the force which binds planets and galaxies together is actually a whisper from a higher dimensional realm. The implications of this are as far-reaching as they are strange. If our universe is a brain floating in a bulk, then other brains could be astonishingly close to us, perhaps mere millimeters away in a higher dimensional direction we cannot point to. These parallel brains would be invisible to us because light carried by photons travels only along our own brain, but gravity leaking through the bulk could provide a potential bridge. A massive object on a nearby brain could exert a subtle gravitational pull on our own world. Some physicists have even speculated that certain unexplained gravitational anomalies could one day be traced back to the influence of a neighboring universe, a parallel sheet of reality just out of reach. This vision of the cosmos as a dynamic, multi-layered structure of colliding and interacting membranes offers a grand new narrative for the history and fate of everything. It suggests that the Big Bang was not a one-time event, but part of a potentially endless cycle of collisions and rebounds in a higher dimensional arena, a cosmic dance of brains that creates and recreates universes across eternity. Having ventured into the realm of colliding brains, we are naturally led to ask a deeper, more fundamental question. What is the nature of this higher dimensional bulk in which these cosmic membranes float? What is the ultimate framework that gives rise to both the brains and the forces that move them? This brings us to one of the most ambitious and mathematically beautiful structures in all of theoretical physics, M-theory, a leading candidate for the holy grail of physics, a theory of everything. M-theory emerges as a powerful synthesis of the 5 different versions of string theory, proposing that they are all just different facets of a single, underlying theory operating in a universe with not 10 but 11 dimensions. This grand vision aims to unify the 2 pillars of modern physics: quantum mechanics, which governs the very small, and general relativity, which governs the very large, into one seamless description of reality. If our universe truly has 11 dimensions, an immediate and obvious puzzle presents itself. Why do we only perceive the 3 dimensions of space and 1 of time? The answer lies in a process known as compactification. Imagine a long, thin garden hose stretched across a field. From a great distance, it appears to be a simple one-dimensional line. But as you move closer, you discover it actually has a second dimension, a circular cross-section. In this analogy, the long length of the hose is like our familiar, extended dimensions of space, while the tiny circular dimension is curled up or compactified, so small that it is invisible to our everyday perception. M-theory proposes that the 7 extra dimensions required by its mathematics are similarly compactified, but instead of being simple circles, they are curled up into shapes of breathtaking complexity and beauty known as Calabi-Yau manifolds. These Calabi-Yau manifolds are not just mathematical curiosities, they are the potential architects of physical reality. Each is a 6-dimensional geometric shape, defined by intricate holes, folds, and twists, existing at every single point in our familiar 4-dimensional spacetime. The specific topology of this hidden geometry, the number of holes, the precise way it is folded, is thought to determine the very laws of physics in our macroscopic world. The way that the fundamental strings of the theory vibrate as they move through the convoluted landscape of a Calabi-Yau manifold dictates what we observe as particles and forces. One specific pattern of vibration might correspond to an electron, another to a quark, and still another to a photon, the particle of light. The shape of the manifold effectively acts like a cosmic musical instrument. A violin string can produce a vast range of notes depending on how it vibrates, and in the same way, a fundamental string can manifest as any particle in nature depending on how it oscillates within the hidden Calabi-Yau dimensions. This leads to a profound and almost magical connection between abstract geometry and the tangible universe. The reason we have exactly 4 fundamental forces and the specific set of elementary particles that we do could be a direct consequence of the exact Calabi-Yau shape chosen by our particular corner of the cosmos during its formation. A differently shaped manifold would produce a completely different set of physical laws with different forces and particles, potentially rendering life as we know it impossible. This provides a geometric explanation for the fine-tuning problem we encountered with the multiverse. In the vast landscape of possible Calabi-Yau shapes, each one a unique 6-dimensional sculpture, only a tiny fraction would yield the stable, complex structures necessary for galaxies, stars, and life to emerge. We exist in a universe built upon one of those rare, harmonious geometric forms. The quest to find the one true Calabi-Yau manifold that describes our reality is one of the greatest challenges in modern theoretical physics, a search for the ultimate geometric signature of our existence, hidden in the sub-microscopic folds of spacetime. While string theory and M-theory weave a reality of extra dimensions and vibrating strings, another profound and powerful theory takes a dramatically different approach to the problem of quantum gravity. It asks a deceptively simple question: what if we don't need extra dimensions or unseen brains at all? What if the key to unifying general relativity and quantum mechanics lies not in adding new layers to reality, but in reimagining the very nature of space and time themselves? This is the promise of loop quantum gravity, a theory that proposes the fabric of the cosmos is not a smooth, continuous sheet, but is instead woven from a tapestry of discrete, indivisible threads. At the heart of this theory is a radical departure from classical physics. In Einstein's general relativity, space-time is a dynamic, malleable continuum. It can curve and warp, but you can always theoretically divide a region of space into smaller and smaller pieces ad infinitum. It's perfectly smooth. Loop quantum gravity challenges this fundamental assumption. It proposes that space itself is quantized. It comes in tiny, discrete, indivisible packets, much like matter and energy. You cannot divide space infinitely. There is a smallest possible unit, a fundamental atom of space, known as the Planck length. This is an almost unimaginably tiny scale, about 10 to the power of -35 meters. To put that in perspective, if you were to magnify a single atom to the size of our entire observable universe, one Planck length would be roughly the height of a single tree on a planet within that universe. At this scale, the smooth geometry we take for granted dissolves into a granular, discrete structure. So, what is space made of if it's not a continuum? The answer is a mesmerizing structure known as a spin network. Imagine the universe not as an empty void, but as an impossibly intricate, ever-changing web. The strands of this web are not made of any material substance. They are one-dimensional lines of gravitational force, or loops. Where these loops intersect, you find nodes. In this model, a volume of space is not defined by its cubic meters, but by the number of nodes in the network within that region. The area of a surface is not measured in square meters, but by the number of loops that pierce through it. Space, in its most fundamental form, is not a container that things exist in. It is a relationship, a vast, interconnected network of these quantized loops and nodes. The familiar, three-dimensional, continuous space we experience in our daily lives is an emergent property, a macroscopic average of this frenetic, quantum-level activity, much like the smooth surface of a pond, emerges from the chaotic motion of countless water molecules. This granular structure of space-time has a breathtaking consequence. It can resolve the most troubling singularities in physics. In Einstein's general relativity, the center of a black hole and the moment of the Big Bang are points of infinite density and curvature, where the laws of physics as we know them break down completely. These are places where the smooth continuum model fails. But in loop quantum gravity, because there is a smallest possible unit of space, matter and energy cannot be compressed into an infinitely small point. There is a limit. This leads to two dramatic predictions. The first is a resolution for black hole singularities. Instead of a point of infinite density, the theory suggests a transition into a region of extreme but finite density, a place sometimes called a Planck star. The second, and even more profound prediction, is a cosmic bounce that replaces the Big Bang. This concept, known as the Big Bounce, paints a picture of a cyclical cosmos. In this view, our universe was not born from a singular creation event from nothing, but from the collapse of a previous cosmic phase. As that prior universe contracted under its own gravity, the density and pressure became immense. But thanks to the discrete nature of space in loop quantum gravity, a point was reached where the repulsive force generated by the quantum geometry became stronger than the attractive force of gravity. Instead of collapsing into a singularity, the universe underwent a tremendous rebound, a bounce, that initiated the expansion we see today. Our entire cosmic history, from the hot, dense early universe to the present day, could be just one cycle in an endless, breathing sequence of expansion and contraction, with each bounce resetting and renewing the cosmos. This elegantly removes the need for a definitive beginning of time, suggesting that the universe may be eternally self-renewing, its hidden spin network constantly evolving and rearranging itself through each cosmic cycle. While the granular structure of loop quantum gravity reshapes our view of cosmic origins, another profound enigma lies in the very emptiness of space. a mystery that reveals a startling gap in our understanding of the universe's fundamental design. This is the cosmological constant problem, and it is arguably the most severe discrepancy between theory and observation in all of modern physics. The puzzle centers on the value of dark energy, the mysterious force driving the accelerated expansion of the cosmos, often represented by a number called the cosmological constant, denoted by the Greek letter lambda. What makes this a problem is not just that dark energy exists, but that its measured strength is so inconceivably tiny that it defies all logical predictions from our most successful theory of the small, quantum field theory. To grasp the sheer scale of this mismatch, we need to look at what quantum mechanics says about empty space. The vacuum is not truly empty, it's a seething, bubbling foam of virtual particles. Pairs of particles and antiparticles constantly blink into and out of existence, borrowing energy from the vacuum for a fleeting moment before annihilating each other. This perpetual, energetic activity should endow every cubic centimeter of empty space with a tremendous amount of energy, a vacuum energy that would act as a powerful repulsive force, causing the universe to expand at a rate too fantastic for galaxies, stars, or atoms to ever form. When physicists calculate the expected contribution of this quantum vacuum energy to the cosmological constant, the result is a number that is, quite literally, off the charts. It is a 1 followed by 120 zeros times larger than the value we actually observe from astronomical measurements. This is not a small error. It is a discrepancy of 1 part in 10 to the power of 120. To call this the worst prediction in the history of science is almost an understatement. It's as if you calculated the weight of a single proton and got an answer equal to the mass of the entire observable universe. This staggering failure is not a sign that our theories are completely wrong, but rather a giant, flashing signpost pointing toward a deep gap in our knowledge. The fact that the measured value of dark energy is so close to zero, yet not exactly zero, suggests there is a hidden mechanism, a fundamental principle or a cancellation effect in the universe's architecture that we have not yet discovered. One of the most discussed ideas for resolving this problem is the anthropic principle, which we encountered in the context of the multiverse. In this view, the cosmological constant is not a fixed derivable number, but a variable that can take on different values in different regions of a vast multiverse. In the overwhelming majority of these regions, the value of lambda is enormous, and the universe either expands so rapidly that no structure can form or it collapses so quickly that life has no chance to arise. We, of course, find ourselves in one of the exceedingly rare pockets where the cosmological constant is minuscule enough to allow for the formation of galaxies and the evolution of conscious observers. In this scenario, the value isn't fine-tuned for us. We are simply the selectors who observe the one value that permits our existence. However, many physicists seek a more fundamental, dynamical explanation rooted in the laws of physics themselves, rather than resorting to anthropic reasoning. Perhaps there is a yet unknown symmetry in nature, a fundamental rule that forces the vacuum energy to cancel itself out to exactly zero. Supersymmetry, a popular theoretical extension of the standard model of particle physics, once offered a glimmer of hope. In a perfectly supersymmetric world, every particle has a superpartner with identical properties but a different spin, and the contributions of these particle pairs to the vacuum energy would perfectly cancel, resulting in a net zero. The problem is, we don't live in a perfectly supersymmetric universe. If it exists at all, supersymmetry is a broken symmetry, meaning the superpartners, if they exist, are much heavier than their ordinary counterparts, and the delicate cancellation is spoiled, leaving us with a large, unexplained remainder. Other proposals suggest that the cosmological constant might not be a fixed property of the vacuum at all, but a dynamic field that can slowly evolve over time, similar to the inflattened field in the early universe. It could be that we are simply observing this field at a particular moment in cosmic history when it has settled into an unusually low energy state. Or perhaps the answer lies in a profound connection between quantum information, gravity, and the holographic principle, where the dark energy we measure is not a local energy density but a global property of the cosmic horizon, a consequence of the finite information content of our observable universe. The cosmological constant problem stands as a silent monument to the limits of our current comprehension. It is a mystery woven into the fabric of nothingness itself, a testament to the fact that even the void holds profound secrets. Solving it would likely require a revolutionary insight that seamlessly unites the quantum world with the cosmic scale, revealing a hidden layer of the universe's structure that currently lies just beyond our grasp. The incredible smallness of dark energy is not an inconvenient detail. It is a profound clue, a whisper from the deepest level of reality, urging us to look closer at the nature of empty space and discover the mechanism that keeps the cosmos balanced on a knife's edge, allowing for the glorious complexity we see around us. We've just been exploring the strange nature of empty space, but now let's turn our attention to a different kind of emptiness, one that is far from empty, but is instead filled with a vast, invisible architecture that holds the entire visible universe together. This is the hidden structure of dark matter. For nearly a century, astronomers have known that the cosmos contains far more than meets the eye. The first clues came from the motions of galaxies within clusters. They were moving so fast that the visible matter alone couldn't possibly provide enough gravity to hold them together. It was as if the stars and gas we could see were just the decorative lights on the surface of a gigantic, unseen iceberg. Later, studies of how individual galaxies spin provided even more dramatic proof. When we look at a spiral galaxy like our own Milky Way, we expect stars on the outer edges to orbit more slowly than those near the bright center, just as Pluto orbits the Sun much more slowly than Mercury does. But that's not what we observe. Stars at the very fringe of a galaxy orbit at almost the same high speed as those near the core. The only plausible explanation is that the entire galaxy is embedded within an enormous, spherical cloud of something that doesn't emit or absorb light, a massive dark matter halo that provides the extra gravitational glue to keep these fast-moving stars from flying off into intergalactic space. These dark matter halos are not just a thin coating, they are the dominant structure of every galaxy. In fact, the glittering, spiral disk of stars and gas that we see in telescope images is just the small, bright nucleus at the center of a gargantuan, invisible sphere of dark matter that can extend 10 times farther out into space. But the true grandeur of this hidden architecture is revealed when we zoom out to the largest scales of the cosmos. These dark matter halos are not isolated. They are connected to one another by even larger, thinner tendrils of dark matter, forming a colossal cosmic web that stretches across the entire universe. This web is the true backbone of the cosmos, a scaffolding upon which the visible universe is built. In the densest knots of this web, where multiple filaments intersect, huge clusters of thousands of galaxies form. Along the filaments themselves, smaller galaxies line up like pearls on a string, and between the filaments are the vast, empty cosmic voids, regions of space almost completely devoid of both dark and visible matter. This magnificent web-like structure is not just a theoretical idea. It has been mapped in stunning detail through its gravitational effects, primarily a phenomenon known as gravitational lensing. Gravitational lensing occurs because anything with mass, including invisible dark matter, warps the fabric of space-time, bending the path of light that travels through it. When astronomers look at distant galaxies, they sometimes see their images stretched, magnified, or distorted into multiple arcs and smears. This happens because the light from those faraway galaxies has passed through the gravitational field of a massive clump of dark matter on its journey to us, like light being bent through a giant, lumpy lens. By meticulously analyzing these distortions across the sky, scientists can essentially trace the distribution of the invisible mass that caused them. They have constructed three-dimensional maps of the dark matter cosmic web, revealing a structure of breathtaking scale and complexity that perfectly aligns with the positions of galaxy clusters and supercomputer simulations of cosmic evolution. These simulations show how, after the Big Bang, the slight gravitational pull of dark matter began to amplify tiny density fluctuations, slowly drawing matter into an interconnected network of filaments and nodes over billions of years. The ordinary matter, the gas that would eventually form stars and planets, simply flowed along this pre-existing dark matter skeleton, collapsing into the halos to create the galaxies we see today. Without this dark matter framework, the universe would be a much darker and emptier place. There would have been no sufficient gravitational wells to gather the gas needed to form the first stars and galaxies, and the cosmos as we know it would never have come to be. So, what exactly is this mysterious substance that makes up roughly 85% of all matter in the universe? The leading hypothesis for decades has been a class of particles known as WIMP, or weakly interacting massive particles. As the name suggests, these are theoretical particles that are thought to be heavy compared to protons and neutrons, and they interact with ordinary matter only through gravity and the weak nuclear force which governs radioactive decay. This would make them incredibly difficult to detect, as they would mostly pass right through the Earth and our detectors without a trace. Physicists have built exquisitely sensitive experiments deep underground, shielded from cosmic rays, in the hope of catching the extremely rare occasion when a WIMP might bump into the nucleus of an atom in their detector. Another compelling candidate is the action, a hypothetical particle that is extremely light, trillions of times lighter than an electron, but which could also exist in such vast numbers that it accounts for the dark matter. Actions were originally proposed to solve a different puzzle in particle physics, but they have properties that also make them a perfect dark matter candidate. Unlike WIMP, actions would interact very weakly with normal matter and would potentially be detected by converting into a faint microwave photon in the presence of a powerful magnetic field. While decades of searching have yet to yield a definitive, direct detection of either a WIMP or an action, the hunt continues with ever more sophisticated experiments, because identifying the true nature of dark matter would not just solve a cosmic mystery. It would open a window into physics far beyond our current standard model, revealing a whole new sector of the universe's hidden population. But what if we've been approaching this entire mystery from the wrong angle? For decades, the dominant assumption has been that we are surrounded by vast amounts of invisible matter. Yet, a bold and persistent alternative challenges this very foundation, suggesting that the hidden structure isn't made of matter at all, but is instead a fundamental flaw in our understanding of gravity itself. This is Theory 11, Modified Newtonian Dynamics, or MND. Proposed by physicist Mordechai Milgrom in the early 1980s, MND asks a revolutionary question: what if dark matter is a phantom, and the real explanation for those flat galaxy rotation curves is that Isaac Newton's famous laws of gravity, while brilliant, simply break down in the extreme weak field environments found in the outer reaches of galaxies and in the depths of interstellar space. At its heart, MND introduces a single, elegant modification. Newton's second law states that force equals mass times acceleration, and this is assumed to hold true everywhere from a falling apple to the orbit of Pluto. But Milgrom suggested that at extremely low accelerations far below what we experience in our solar system, this relationship changes. He proposed a new, tiny acceleration scale, a threshold below which gravity ceases to behave in the way Newton and Einstein described. When the gravitational acceleration acting on a star drops below this critical value, which is about 100 billion times smaller than the gravity we feel on Earth, the force of gravity begins to fall off more slowly than the traditional inverse square law would predict. It's as if gravity gets a second wind, becoming stronger than expected in these faint, far-flung regions. This simple tweak has a profound and direct consequence. It naturally predicts that stars orbiting at the edges of galaxies should experience a stronger gravitational pull than standard physics would allow, causing them to move faster, which is exactly what we observe in those mysteriously flat rotation curves. In the Mund paradigm, there is no need for a massive, invisible halo of dark matter. The observed motion of the stars is explained by the behavior of gravity itself. The appeal of Mund lies in its stunning predictive power on galactic scales. Unlike the dark matter model, which often requires complex computer simulations to tune the distribution of dark matter in each individual galaxy to match its rotation curve, Mund often succeeds with remarkable precision using only the visible matter we can see. It has successfully predicted the rotation curves of many galaxies based solely on their distribution of stars and gas, a feat that is difficult for the dark matter model to replicate without making additional assumptions. Beyond rotation curves, Mund also offers elegant explanations for other galactic puzzles. For instance, it can account for the observed relationship between a galaxy's brightness and its rotation speed, known as the baryonic-Tully-Fisher relation, a tight correlation that emerges naturally from Mund equations but is less directly explained in the dark matter framework. For many of its proponents, this elegance and predictive success is a strong indicator that Mund is pointing toward a deeper truth about the fundamental nature of gravity, suggesting that our current theories are incomplete descriptions of reality, much like Newtonian gravity was an incomplete description before Einstein's theory of general relativity came along. However, the story is far from one-sided, and the mainstream cosmological community remains largely unconvinced, primarily because of Mund's significant struggles when we zoom out from individual galaxies to the scale of entire galaxy clusters and the cosmic web. While Mund can explain the internal dynamics of a single galaxy, it has a much harder time accounting for the observed gravitational pull of massive galaxy clusters. When astronomers measure the total mass of a cluster by observing how its gravity bends light from background galaxies, a technique called gravitational lensing, they find an immense amount of mass that is simply not present in the visible stars and hot gas. In the standard model, this is compelling evidence for the dark matter halo surrounding the entire cluster. In a pure Mund framework, the modified gravity alone is often not sufficient to explain the strength of this lensing effect. To bridge this gap, some Mund proponents have had to suggest that there might still be some form of unseen matter in these clusters, though it would be different from the cold dark matter particles typically invoked, perhaps consisting of neutrinos with a small amount of mass. The most formidable challenge for Mund, however, comes from the grandest cosmic collision ever observed, the Bullet Cluster. This system consists of two galaxy clusters that have violently passed through one another. The crucial observation is that the bulk of the visible mass in the form of hot, X-ray emitting gas was slowed down and stuck in the center of the collision due to friction, much like two clouds of smoke would intermingle. But the gravitational mass, as mapped by gravitational lensing, did not slow down. It continued on, separated from the visible gas. This is interpreted as direct evidence that most of the mass is in a form that does not interact with itself or with normal matter other than through gravity, a perfect description of collisionless dark matter. For many, the Bullet Cluster is a smoking gun, seemingly demonstrating the existence of dark matter as a substance that can be physically separated from visible matter. Advocates for Mund have developed complex extensions to the theory to try and explain this separation, but these models often lose the simple elegance that made original Mund so attractive, requiring additional fields and assumptions that begin to resemble the complexity of the model they seek to replace. So, where does this leave us in the great debate over the universe's hidden architecture? We are faced with two radically different interpretations of the cosmos. On one side stands the overwhelmingly dominant lambda cold dark matter model, which posits an invisible universe of exotic particles that form a cosmic web, providing the gravitational scaffolding for everything we see. This model is incredibly successful at explaining the large-scale structure of the universe, from the patterns in the cosmic microwave background to the distribution of galaxies. On the other side stands MUND and its relativistic extensions like tensor vector scalar gravity, which argue that we have misunderstood gravity itself, and that by correcting this fundamental force, we can explain the data without the need for vast amounts of unseen matter. This is not merely a technical disagreement, it is a profound philosophical divide. Is the cosmos filled with hidden stuff, or are we operating with hidden, incomplete laws? The future of this debate likely rests on new, decisive observations. As we build more sensitive detectors to hunt for dark matter particles and launch more powerful telescopes to map the cosmos in greater detail, we may finally get an answer. The resolution will not just tell us what holds galaxies together. It will reveal whether the greatest hidden structure in the universe is made of matter or is written into the very rules of space, time, and motion. Leaving behind the debate over dark matter and modified gravity, we now turn our gaze to the very oldest light in the universe, a cosmic fossil that has been traveling for over 13 billion years to reach us. This is the cosmic microwave background, or CMB, the faint, cold afterglow of the Big Bang itself. Imagine the universe in its infancy, a seething, opaque plasma of particles and energy, so dense that light could not travel freely. Then, about 380,000 years after the initial expansion began, the cosmos had cooled enough for atoms to form, allowing light to finally break free and stream across the universe. That first flash of light, now stretched and cooled by the universe's relentless expansion, reaches us today as a microwave whisper, a nearly uniform glow that fills every direction of the sky. It is the most perfect blackbody radiation ever measured, a snapshot of the infant cosmos, and for the most part, it confirms our standard model of cosmology with stunning precision. Its tiny, random fluctuations in temperature variations of mere millionths of a degree represent the seeds of all future structure, the slightly denser regions that would eventually collapse under gravity to form galaxies and clusters. Yet, when scientists probe this ancient map with ever-increasing sensitivity, most notably with the Planck satellite, they discovered a few features so strange and unexpected that they have been given dramatic names like the axis of evil, suggesting that our cosmic blueprint might contain a few cryptic notes we don't yet understand. The most prominent of these mysteries is the so-called axis of evil. This isn't a literal axis in space, but a startling statistical alignment. According to the foundational cosmological principle, the universe should be isotropic and homogeneous, meaning it should look roughly the same in every direction, with no preferred axis or special center. The patterns in the CMB should be random and uncorrelated, like a static-filled television screen. But when researchers analyzed the data, they found that the largest scale fluctuations in the microwave background, the waves that stretch across billions of light years, appear to be aligned along a particular direction in space. It's as if the universe has a faint preferred plane, much like the ecliptic plane of our solar system. This apparent alignment defies the expectation of randomness. Some scientists have proposed that this could be a sign of something profound, perhaps a remnant imprint from a time before the Big Bang, a structure or a dynamic that influenced the very birth of our cosmos. Others have even speculated it could be a hint that our universe is not infinite, but has a complex, non-trivial topology, like a hall of mirrors on a cosmic scale, where space connects back on itself in a way that creates patterns we interpret as an alignment. Alongside this mysterious axis, another profound anomaly captures the imagination, the CMB cold spot. This is a large, circular region in the southern galactic hemisphere that is significantly colder than the surrounding average. It's not just a little bit cold, it is a colossal feature about 1.8 billion light-years across, and its temperature is so unusually low that the probability of it occurring by random chance in a standard universe is extremely small. One compelling, if speculative, explanation is that the cold spot is not a feature of the CMB itself, but is caused by an enormous cosmic void, a vast underdensity of both dark and visible matter lying between us and the CMB. As light from the primordial glow passes through such a void, it could lose energy climbing out of the void's weaker gravitational potential, a phenomenon known as the integrated Sachs-Wolf effect, creating a cold imprint on the map. If this is the case, the cold spot would be evidence of one of the largest structures ever identified in the universe. However, exhaustive surveys have struggled to find a void large enough and empty enough to explain the cold spot's profound chill, leaving this explanation in doubt. This has led to even more exotic proposals. Some theorists suggest the cold spot could be the signature of a collision with another universe in the multiverse. In the brain cosmology model we discussed earlier, such a collision could have transferred energy away from a region of our universe, leaving it cooler. Another possibility is that it is a topological defect, like a super-sized cosmic texture, a knot in the fabric of space-time that formed as the universe cooled and left a permanent scar on the CMB. The debate over these anomalies is a fascinating display of the scientific process at work. The majority of cosmologists maintain that these features, while intriguing, are likely just statistical flukes. They argue that when you look at any rich dataset, you are bound to find a few seemingly improbable patterns. It's the cosmic equivalent of seeing shapes in the clouds. They point out that the overall consistency of the CMB with the standard model is so overwhelming that overturning it based on a few anomalies would be premature. Yet, a persistent minority continues to investigate, convinced that these are not mere ghosts in the data, but genuine clues pointing toward a deeper, more complex cosmic origin story than we have yet imagined. They are the cosmic detectives scrutinizing this ancient map for tiny cracks in our standard model, believing that within these flaws in the fossilized light, we might just find the key to the next great revolution in our understanding of everything. Building on the idea of hidden cosmic structures, we encounter a theory that proposes a remarkably simple yet elegant solution to the dark matter puzzle. What if the invisible mass holding galaxies together isn't a sea of exotic, undiscovered particles, but a vast population of ancient, primordial black holes? These aren't the stellar mass black holes formed from dying stars or the supermassive giants at galactic centers. Primordial black holes, or PBH, are theorized to have been forged in the extreme density and pressure of the universe's very first second, born from the raw chaos of the Big Bang itself. In that frantic, expanding infant cosmos, regions of space that were just slightly denser than their surroundings could have collapsed directly under their own intense gravity, pinching off into black holes without the need for a single star to ever form. This idea transforms the dark matter halo of a galaxy from a diffuse cloud of unknown particles into a bustling swarm of these primordial fossils, each one a relic from the dawn of time, silently orbiting the galactic center. The appeal of this theory lies in its ability to solve two profound mysteries with one elegant concept. First, it directly addresses the dark matter problem. A sufficiently large population of these primordial black holes, distributed throughout a galaxy's halo, would provide all the gravitational pull needed to explain the high orbital speeds of stars and the powerful lensing effects we observe, all while remaining completely dark and invisible to our telescopes. Second, it offers a potential origin story for some of the black holes we are beginning to detect through gravitational wave observatories like LIGO and Virgo. The collisions between surprisingly heavy black holes that these instruments have recorded could be explained if the participants were not stellar remnants, but these ancient primordial black holes from the universe's infancy, finally merging after billions of years in a cosmic dance. Detecting these elusive objects, however, is a tremendous challenge. since they don't emit light, we can only find them through their gravitational influence. Astronomers are conducting a kind of cosmic fishing expedition, searching for PBHs across a vast range of possible masses. On the smaller end of the scale, they are looking for black holes with masses similar to asteroids or small planets. A key method here is gravitational microlensing. If a primordial black hole in our galaxy's halo were to pass directly in front of a distant star, its gravity would act as a tiny lens, bending the star's light and causing it to temporarily brighten in a very specific, recognizable way. Vast surveys monitoring millions of stars have indeed found such microlensing events, but the number detected so far is far too small to account for all the dark matter. This has largely ruled out the possibility that the primary component of dark matter is a huge number of planet-sized black holes. The search then moves to larger mass ranges. Scientists are looking for primordial black holes with masses comparable to stars, from a few times the mass of our Sun up to 1,000 solar masses. These could be detected by their impact on the delicate structures within galaxies, such as the disruption of fragile star clusters or the subtle distortions they would create in the smooth streams of stars that orbit the Milky Way. The most massive end of the spectrum considers PBHs that could be thousands of times heavier than the Sun, potentially acting as the invisible seeds around which the supermassive black holes at the hearts of galaxies later grew. Each of these mass windows presents a different set of observational tests, and so far, no single population has been found in sufficient abundance to explain all the dark matter. Yet the possibility remains that dark matter is not a single thing, but a mix of different objects with primordial black holes of various sizes contributing a significant portion. The hunt continues, a meticulous process of elimination across the mass spectrum, probing the dark halo of our galaxy for the subtle, gravitational whispers of these primordial architects. This leads us to a theory that completely redefines the concept of a beginning, suggesting our universe's origin was not a singular, explosive event from nothing, but a magnificent rebound from a prior cosmic era. This is the Big Bounce, a cornerstone of cyclic models that portrays our cosmos as an eternally breathing entity. In this view, the Big Bang was not the start of time, but the turning point, the moment a great cosmic contraction reversed into the expansion we witness today. This paints a picture of a universe with a hidden temporal structure, an endless rhythm of birth, death, and rebirth on a scale so vast it challenges our very understanding of existence. To grasp how such a bounce is possible, we must return to the granular nature of reality proposed by loop quantum gravity. In Einstein's smooth continuum, a collapsing universe would be doomed to squeeze itself into an infinitely dense, infinitely hot singularity, a point where physics breaks down and the story ends. But loop quantum gravity introduces a quantum repulsion that arises from the discrete nature of space itself. As the previous universe contracted, matter and energy were compressed to unimaginable densities. However, when the scale approached the tiny Planck length, the fundamental grain of space, the quantum geometry of the spin network would have generated a tremendous repulsive force. Think of it like compressing a spring. You can push it down, but at a certain point, the spring's inherent resistance becomes stronger than the force you're applying, and it pushes back, rebounding with immense energy. In the cosmic context, this quantum repulsion would have overcome the attractive crush of gravity, causing the entire universe to bounce back outward, initiating the hot, dense state we call the Big Bang. This elegant mechanism not only avoids the troubling singularity, but also provides a natural, physical reason for the expansion to begin, all without requiring a supernatural starting gun. This cyclical vision isn't confined to a single theoretical framework. Within the brain cosmology scenario we explored earlier, a profoundly different kind of cyclic model emerges, driven not by a quantum bounce but by a rhythmic dance of parallel worlds. In the ekpyrotic model, our three-dimensional brain exists in a higher dimensional bulk alongside at least one other parallel brain. Instead of a single creation event, this model proposes an endless cycle of attraction, collision, and separation. The cycle begins with the two brains drawn together across the bulk. Their collision is not destructive, it is generative. The immense kinetic energy of the impact is converted into the heat and radiation that floods our brain, creating the conditions for a new cosmic cycle, our Big Bang. After the collision, the brains bounce apart, and the universe within each one expands and cools, allowing galaxies and stars to form over billions of years. Eventually, the expansion slows, stops, and reverses, drawn by a mysterious force perhaps related to a dark energy field, pulling the brains back together for another collision and another rebirth. In this model, the hidden temporal structure is not just a timeline, but a higher dimensional orbit, a cosmic waltz of universes that has been repeating for eternity. The implications of these cyclic models are as philosophical as they are physical. They remove the need for an absolute beginning, suggesting that time itself may be infinite, with no first cycle and presumably no last. Our entire cosmic history, from the first glimmer of light after the bounce to the formation of our solar system and the rise of life on Earth, becomes just one chapter in an endless repeating saga. Each cycle or eon might last trillions of years with its own unique history and potentially even different physical constants, depending on the specific bounce dynamics. This provides a breathtaking new perspective on our place in the cosmos. We are not living in a one-and-done universe with a definitive start and a potentially bleak end. We are part of an eternal process of renewal. The death of our universe in a far future Big Crunch would not be an ultimate finale, but merely the prelude to a subsequent grand rebirth, a cosmic phoenix rising from its own ashes to begin the story anew. Naturally, such a grand proposal faces significant questions and challenges. A major hurdle for traditional cyclic models has been the second law of thermodynamics, which states that entropy or disorder always increases. If each cycle inherited the accumulated entropy from the previous one, the universe would become more disordered with every bounce, and we would not see the low entropy, highly ordered state from which our universe clearly began. However, some modern cyclic models, particularly those involving brain collisions, offer a potential solution. They suggest that during the collision and bounce phase, the universe is effectively heated up and reset. The immense energy and turbulence of the collision could randomize everything, wiping the cosmic slate clean and restoring a low entropy, high energy state for the next cycle to begin. It's analogous to shaking a snow globe vigorously. All the settled flakes are thrown back into a chaotic, high energy state, ready to settle once more. While the ultimate feasibility of these models is still a subject of intense research and debate, they stand as a powerful testament to the human imagination's capacity to conceive of a cosmos without beginning or end, a universe whose greatest hidden structure may be the timeless, cyclical rhythm of its own existence. But if the cyclical universe offers a hidden structure in time, the next theory we explore proposes that the ultimate hidden structure of everything is not made of matter, energy, or even space-time, but of pure, abstract mathematics. This is the mathematical universe hypothesis, a breathtakingly ambitious idea championed by cosmologist Max Tegmark. It pushes the relationship between mathematics and physics to its ultimate logical extreme. We are accustomed to the powerful idea that the universe is described by mathematics, that we can use equations to predict the motion of planets or the behavior of particles with uncanny accuracy. But Tegmark's hypothesis goes much further. It states that our physical reality is a mathematical structure. In other words, the universe isn't just running on a set of mathematical rules like a computer following a program. The universe is that program, and its existence is equivalent to the mathematical truth of that structure. To grasp this, consider a simple, timeless mathematical object, a perfect cube. According to Euclid's geometry, a cube has a specific, well-defined set of properties. It has 6 square faces, 12 edges, and 8 vertices. These relationships are true, regardless of whether anyone is thinking about them or a physical cube exists somewhere to represent them. The mathematical universe hypothesis asserts that this cube, as a mathematical structure, does indeed exist in a physical sense. It exists not in our space-time, but as one of countless mathematical structures that constitute reality. Now, scale this idea up from a simple cube to an infinitely more complex mathematical structure, one that defines relationships between entities that behave like space, time, and fields. Tegmark argues that our own universe is precisely such a structure. The laws of physics we have discovered, from general relativity to the Standard Model, are not just approximations of an underlying reality. They are the reality, representing the immutable mathematical relationships that define our particular structure. This leads to a staggering conclusion that forms the core of the hypothesis. Every mathematically consistent structure exists in a physical sense. If a set of mathematical axioms and relationships is free from internal contradictions, then a universe governed by those rules is real. This creates a multiverse of a kind far more vast and fundamental than any we have discussed so far. It is not just a multiverse of different physical constants or quantum branches, but a multiverse of entirely different mathematical laws. There would be universes where the rules of Euclidean geometry hold perfectly at all scales, and others where hyperbolic geometry is the norm. There would be structures with thousands of spatial dimensions, universes where time flows in 2 directions, and realities built on mathematical foundations we haven't even begun to conceive. In this ultimate ensemble, our cosmos is just one relatively simple mathematical structure among an infinite and unending menagerie of possibilities. The implications for our own existence within this framework are deeply philosophical and force us to reconsider the nature of consciousness itself. If our universe is just a mathematical structure, then what are we? Our thoughts, our sensations, and our sense of self must also be part of this structure. Tegmark and others suggest that consciousness itself is a particular kind of complex, self-aware substructure within the larger mathematical system. It is a pattern, a highly sophisticated algorithm for processing information that has the subjective experience of being. From this perspective, you are not a ghost in the machine. You are the machine, or more precisely, you are a specific, self-referencing part of the cosmic mathematical equation that has become aware of its own existence. Your life is the process of this subsystem, your consciousness, traversing a tiny, specific path through the vast state space of possible configurations allowed by our universe's mathematical rules. This viewpoint provides a radical, almost unsettling answer to the famous question of why mathematics is so unreasonably effective at describing the natural world. The answer, according to this hypothesis, is simple. There is no distinction between the natural world and the mathematics. They are one and the same. The reason a physicist can write down an equation that predicts a new particle is not because nature is obeying a mathematical law, but because the physicist is uncovering a piece of the structural blueprint of which they themselves are a part. This removes any need for external, non-mathematical reality. Everything that exists, from the flight of a bird to the spin of an electron to the birth of a galaxy, is a manifestation of mathematical truth. The mathematical universe hypothesis is perhaps the ultimate expression of the search for hidden structures, suggesting that when we peel back all the layers of reality, we won't find strings, brains, or quantum loops, but only the eternal, Platonic realm of mathematics, of which we are a fleeting, self-aware expression. From the timeless realm of abstract mathematics, we now return to the tangible, quantum world to explore a discovery so strange it seems to redefine the very nature of motion and time. This is the world of time crystals, a completely new phase of matter that was once deemed a physical impossibility. For centuries, the dream of a perpetual motion machine has been a fool's errand, a violation of the fundamental laws of thermodynamics. Any system that moves will eventually run down, its energy dissipating as heat until it reaches a dead, motionless state of equilibrium known as its ground state. But in 2016, physicists conceived of, and soon after created, a system that turns this intuition on its head. A structure that exhibits perpetual, periodic motion even in its ground state, achieving a form of perpetual motion that is perfectly allowed by the laws of quantum mechanics. To understand this marvel, we first need to grasp what a time crystal is and what it isn't. It's not a shiny gem that travels through time. Think of it instead as a hidden temporal structure, a system whose components are arranged in a pattern that not only repeats in space, like the atoms in a regular crystal, but also repeats in time. An ordinary crystal, like a diamond, has a structure that is symmetrical in space. If you shift your perspective by the width of one atom, the arrangement looks the same. It has what's called spatial symmetry. But if you try to shift it by half an atom, the symmetry is broken, the pattern looks different. A time crystal does something analogous for time. In a normal system at rest, if you take a snapshot and then take another snapshot a moment later, nothing has changed. It has time translation symmetry. A time crystal, however, spontaneously breaks this symmetry. It has a natural, preferred tick-tock rhythm. Even in its ground state, its most minimal energy configuration, it will not sit still. Its components, be they atoms or ions or quasi-particles, will periodically return to their starting positions over a fixed cycle, oscillating forever without any energy input or loss. It's as if you had a clock that, once wound, would tick forever without ever needing to be rewound. Its hands moving in a ceaseless dance driven not by stored energy, but by the intrinsic quantum structure of the system itself. Creating such a system in the real world required immense ingenuity. The original theoretical work by Nobel laureate Frank Wilczek proposed a time crystal in permanent equilibrium, which later analysis showed was not feasible. The breakthrough came with the concept of the Floquet time crystal, a system that is periodically kicked by an external laser or electromagnetic pulse. In a normal system, if you drive it at a certain frequency, it will respond at that same frequency, but in a time crystal, something magical happens. The system responds at a fraction of that frequency, establishing its own, slower, intrinsic rhythm. For instance, if scientists pulse a chain of ions with a laser at a regular interval, the ions might only complete one full cycle of their own internal motion for every 2 pulses of the laser. This subharmonic response is the telltale signature of a time crystal. It's a robust, stable state of matter that is remarkably resistant to perturbations and noise, a quantum dance that persists in the face of the disorder that normally brings all motion to a halt. The potential applications of this are as revolutionary as the concept itself. The remarkable stability of time crystals makes them a prime candidate for the heart of a new generation of quantum computers. One of the biggest challenges in quantum computing is decoherence, the tendency for fragile quantum states to be disrupted and lose their information by interacting with their environment. A time crystal's persistent periodic rhythm could provide a protected, stable beat against which quantum operations could be synchronized, acting as a perfect quantum memory or a fault-tolerant clock for a quantum processor. This could be the key to building large-scale, practical quantum machines that can solve problems far beyond the reach of today's most powerful supercomputers. But beyond their technological promise, time crystals may hold even deeper significance for our understanding of the cosmos. Their existence hints at a new kind of order in the universe, one that is intrinsically dynamical rather than static. For centuries, physics has described the fundamental layers of reality in terms of static fields and particles. Time crystals suggest that at the most fundamental level, there could be structures that are inherently rhythmic, that time itself may not be a mere stage on which events play out, but an active participant with its own crystalline structures. Could there be cosmological time crystals, vast quantum systems formed in the early universe that are still oscillating today, their subtle rhythms influencing the large-scale structure of space-time? It's a speculative but thrilling possibility. The discovery of time crystals has opened a new chapter in physics, revealing that even in the state of lowest energy, the universe is not asleep. It is quietly, perpetually ticking, suggesting that motion and rhythm may be as fundamental to reality as space and matter. Now we come to a puzzle that strikes at the very heart of our understanding of reality, a conflict so profound that it has divided physicists for decades. This is the black hole information paradox, and it forces us to confront a fundamental clash between our two most successful theories: the deterministic, reversible world of quantum mechanics and the smooth, causal geometry of Einstein's general relativity. At its core, this paradox asks a deceptively simple question with staggering implications. When something falls into a black hole, what ultimately happens to the information that described it? According to the quantum rulebook, the answer should be nothing at all. Information must be preserved. It can be scrambled, transformed, and rendered utterly unrecognizable, but it can never be truly erased from the universe. This principle of unitarity is the bedrock of quantum physics, ensuring that the past is always, in principle, recoverable from the present. Yet, black holes seem to offer a monstrous exception to this rule. The problem was crystallized by Stephen Hawking's groundbreaking work in the 1970s. He showed that black holes are not completely black. Due to bizarre quantum effects occurring right at the edge of the event horizon, they slowly radiate energy, emitting a faint glow of what we now call Hawking radiation. This radiation carries energy away from the black hole, causing it to slowly lose mass and over trillions of years completely evaporate, vanishing from the universe. Here lies the paradox. Hawking's original calculation suggested that this radiation is purely thermal, a random, featureless hiss of heat. It contains no information whatsoever about the specific things that fell in, whether it was a star, a library of books, or a collection of elementary particles. So, if the black hole evaporates into this random radiation and disappears, then all the detailed information about everything that ever crossed its event horizon has been irrevocably lost from the universe. It's as if you burned a complex, detailed instruction manual, and all that was left was a pile of identical, blank ashes. The manual's information is gone, violating the most sacred principle of quantum theory. This suggests that our universe is fundamentally unpredictable, that history can be erased, a conclusion that most physicists find deeply unsettling. One of the most mind-bending proposals to resolve this is the principle of black hole complementarity, championed by physicists like Leonard Susskind. This idea asks us to accept a profound kind of cosmic censorship. It states that from the perspective of an outside observer, information never actually falls into the black hole. Instead, it gets scrambled, heated to an incredible temperature, and smeared across the event horizon's surface, where it is then slowly and meticulously encoded into the outgoing Hawking radiation. From this external viewpoint, the horizon acts like a fiery membrane, a holographic screen that preserves all information. However, from the perspective of an astronaut foolishly falling into the black hole, nothing special happens at the horizon. They pass through it smoothly, according to Einstein's equations, carrying their information with them into the black hole's interior. Black hole complementarity asserts that both of these stories are correct in their own reference frames, and the paradox is avoided because no single observer ever witnesses a contradiction. You can have information both reflected at the horizon and passing through it, just not for the same observer at the same time. It's a concept that forces us to abandon the classical notion of a single, objective reality and accept that the fate of information depends entirely on who is looking. An even more radical and elegant solution comes from the ER equals EPR conjecture. This proposal, which sounds more like a mathematical formula than a physical idea, was put forward by Juan Maldacena and Leonard Susskind. It forges a stunning link between two concepts that were previously thought to be entirely separate: quantum entanglement and the fabric of spacetime. The ER part refers to an Einstein-Rosen bridge, which is the formal name for a wormhole, a hypothetical tunnel through spacetime connecting two distant points. The EPR part refers to Einstein, Podolsky, and Rosen, the physicists who first highlighted the bizarre, spooky action at a distance of quantum entanglement, where two particles can share a connection that instantly correlates their states no matter how far apart they are. The conjecture proposes that these two ideas are one and the same. When two particles are intricately entangled, they are not communicating faster than light. They are, in fact, connected by a microscopic wormhole, a tiny bridge in the geometry of spacetime itself. This has a breathtaking implication for the information paradox. Imagine two particles falling into a black hole from different directions. In the old view, their information is lost inside. But in the ER equals EPR picture, all the particles that have ever fallen into the black hole could be intricately entangled with the particles that make up the Hawking radiation being emitted outside. These entanglement connections would form a vast, complex network of microscopic wormholes, weaving the black hole's interior together with its external radiation. When the black hole finally evaporates, it doesn't vanish, leaving disconnected radiation behind. Instead, the interior is not a separate place at all. It is geometrically connected to the outside via this web of wormholes. The information that seemed to be trapped inside was, in reality, always encoded in the relationships, the entanglement between the Hawking radiation particles. There is no singularity where information is destroyed because the fabric of spacetime, at its most fundamental level, is built from and defined by these quantum connections. The black hole's evaporation is not a destruction but a transformation, an unraveling of a complex quantum state where all information is preserved in the tangled web of correlations left behind. These proposed solutions, while brilliant, all point toward one inescapable conclusion. The paradox is not a flaw in our theories, but a giant signpost pointing to a hidden layer of reality. Our comfortable understanding of spacetime as a smooth, continuous stage is an illusion that breaks down under the extreme conditions of a black hole. The true, fundamental nature of reality likely resides at the mysterious Planck scale, where the concepts of space, time, and information become inextricably intertwined. The black hole information paradox is our most powerful guide into this unknown territory, forcing us to invent new concepts like complementarity and to see profound unity in ideas we once thought were separate. Solving it won't just tell us what happens to information. It will reveal the hidden quantum gravitational architecture from which the universe itself is woven. After exploring the intricate dance of black holes and information, we venture into a structure that represents the ultimate cosmic shortcut, the wormhole formerly known as an Einstein-Rosen bridge. This theoretical passageway is a direct prediction of Einstein's theory of general relativity, a solution to his field equations that suggests the fabric of spacetime could be folded, creating a tunnel that connects two otherwise distant regions. Picture the universe not as a flat sheet but as a crumpled piece of paper. If you were an ant constrained to walk along the surface from one point to another, your journey would be long. But if the paper were folded, bringing those 2 points almost into contact, a tiny bridge could connect them, creating a shortcut through the higher dimension. A wormhole is precisely that kind of bridge, but for the fabric of reality itself, offering a conduit that could, in principle, link stars millions of light years apart, or even bridge the gap between entirely different universes. The anatomy of a traversable wormhole consists of at least two distinct parts. First, there are the two mouths, each one appearing as a spherical portal, potentially resembling a black hole but without a crushing singularity at its center. Second, there is the throat, the tunnel-like structure that connects these two mouths. What makes this concept so fantastically alluring is the potential for travel. An object entering one mouth could theoretically exit the other almost instantaneously, sidestepping the vast cosmic distances and the limitation of light speed that defines our conventional understanding of travel. The visual phenomenon associated with such a structure is as beautiful as it is bizarre. As depicted in stunning films like Interstellar, the view through a wormhole's mouth would be a warped fish-eye lens onto the destination, with the entire background galaxy stretched and distorted into a brilliant, swirling ring of light due to the extreme gravitational lensing around the throat. This isn't just artistic license, it's a direct consequence of how such a massive object would bend the paths of light from the world on the other side. However, the dream of using a wormhole for interstellar travel immediately collides with a harsh physical reality. They are almost certainly unstable. The original Einstein-Rosen bridge, derived from the equations for a black hole, was not a tunnel one could ever hope to traverse. It would form and then pinch shut or collapse faster than even a beam of light could pass through, effectively sealing the exit and crushing anything inside. To transform this mathematical curiosity into a stable, traversable highway, physicists have theorized that you would need a truly exotic substance to act as scaffolding, holding the throat open against its own intense gravitational tendency to collapse. This hypothetical material is known as exotic matter, and its defining property is that it would possess negative energy density or negative pressure. Unlike everything we encounter in our daily lives, which has positive energy and creates attractive gravity, this exotic matter would generate a repulsive gravitational effect, physically propping the wormhole's throat open and preventing its catastrophic closure. The challenge, of course, is that such exotic matter has never been observed in a stable macroscopic form. Certain quantum effects, like the Casimir effect, demonstrate that regions of negative energy density can exist on a subatomic scale, where the quantum fluctuations of the vacuum are suppressed between two closely spaced plates. But scaling this fleeting, microscopic phenomenon up to the astronomical levels needed to stabilize a wormhole large enough for a person, let alone a spaceship, is a problem of monumental proportions. Without a known source of this exotic matter, traversable wormholes remain firmly in the realm of theoretical possibility. Yet their value to physics extends far beyond the dream of faster-than-light travel. They have become powerful conceptual tools, offering profound insights into the deepest mysteries of the universe. One of the most revolutionary of these insights is the ER equals EPR conjecture, an idea we touched upon with black holes. This proposal creates a stunning bridge between the geometry of spacetime and the quantum phenomenon of entanglement. ER refers to the Einstein-Rosen bridge, or wormhole, while EPR refers to the famous thought experiment by Einstein, Podolsky, and Rosen that highlighted the spooky action at a distance of quantum entanglement. The conjecture boldly suggests that these two seemingly disconnected concepts are, in fact, two different descriptions of the same underlying reality. When two particles are quantum entangled, their fates are inextricably linked. Measuring the state of one instantly tells you the state of the other, regardless of the distance separating them. ER equals EPR proposes that this mysterious, instantaneous connection is not a ghostly influence traveling through space, but is actually facilitated by a microscopic wormhole linking the two particles. The particles aren't communicating faster than light. They are, in a geometric sense, right next to each other, connected by a tiny, sub-microscopic tunnel in the fabric of spacetime. This perspective completely reframes our understanding of connectivity in the cosmos. It suggests that the fabric of spacetime itself, which appears smooth and continuous to us, may be woven together from an unimaginably dense network of these tiny quantum wormholes, a vast, hidden architecture of entanglement that stitches the universe into a coherent whole. In this view, what we perceive as empty space is anything but empty. It is a vibrant, dynamic tapestry of quantum connections, each one a microscopic bridge. This idea provides a compelling geometric picture for how information could escape a black hole without violating any laws. The Hawking radiation particles emitted from a black hole could be intricately entangled with the particles inside it, and that entanglement would consist of a web of these microscopic wormholes, ensuring that the information is never truly lost, just reconfigured. The wormhole, once a fantasy of science fiction, thus emerges as a potential cornerstone for a theory of quantum gravity, revealing that the hidden structure of the universe might be a deeply interconnected network where quantum information and spacetime geometry are fundamentally inseparable. Having journeyed through the labyrinth of wormholes, we now arrive at a concept that is, in many ways, its perfect theoretical mirror, the white hole. If a black hole is a cosmic drain from which nothing can escape, a white hole is its hypothetical opposite, a cosmic fountain, a region of spacetime that cannot be entered from the outside, but from which matter and light can only ever pour forth. It is an eruption of space, time, and energy into the universe, a one-way door that only opens outward. The mathematics of Einstein's general relativity, which so elegantly predicts the existence of black holes, is perfectly symmetrical and allows for this equally bizarre solution. Where the black hole's event horizon is a point of no return for anything falling in, the white hole's horizon is a point of no entrance for anything trying to get in from the outside. It would violently repel any matter or radiation that approached it, while simultaneously spewing out its own contents into the wider cosmos. While the equations permit such an object, the physics of our universe seem to conspire against its natural formation. The most powerful argument against white holes comes from the second law of thermodynamics, the universal principle that disorder or entropy always increases. A white hole would essentially be a machine that decreases entropy, taking in nothing and creating order out of seemingly nothing, which is a profound violation of this most fundamental rule. Furthermore, for a white hole to form, you would need a set of initial conditions that are perfectly tuned to produce this explosive outflow without any preceding collapse, a scenario most physicists consider impossibly unlikely. If one were to somehow create a white hole, it would be spectacularly unstable. Any single particle of matter or dust that managed to fall onto it, which would be inevitable in our universe, would be enough to collapse the entire structure, triggering its transformation into a black hole. For all these reasons, white holes are generally regarded as mathematical curiosities rather than actual astrophysical objects we might one day observe. Yet, the theoretical appeal of white holes is so powerful that physicists continue to explore their potential roles in more exotic scenarios. One of the most compelling ideas connects them directly to the origin of everything. Some cosmologists have speculated that the Big Bang itself could be viewed as a primordial white hole event, a colossal, singular eruption of space-time and energy from a previous state. In this view, our entire universe isn't just the aftermath of an explosion. It is the interior of a white hole, born in a single, definitive act of creation. This provides a fascinating, though highly speculative, alternative to the cyclical bounce models, suggesting a single, asymmetric beginning where our cosmos burst forth from a gateway connected to a prior, perhaps inaccessible, reality. Another profound connection lies in the relationship between black holes and white holes through the lens of quantum gravity. In some interpretations of loop quantum gravity, the terrifying singularity at the center of a black hole is replaced by a bridge to a new region of spacetime. As the black hole evaporates via Hawking radiation and approaches its final moments, this quantum repulsion might not just cause a bounce but a dramatic transition. The interior of the dying black hole could tunnel through a quantum gravitational barrier and emerge as a new, budding universe, a white hole on the other side. From the perspective of an observer in our universe, the black hole simply evaporates and vanishes. But from an internal perspective, the collapse reverses into an expansion, creating a new cosmic realm with its own space-time, completely disconnected from our own. In this breathtaking vision, every black hole in our universe could be the seed of a new cosmos, a birthing chamber for an entire reality, making our universe a fertile matrix within an endless, branching multiverse of descendant universes. Whether as a description of the Big Bang or as the secret destiny of every black hole, the white hole represents one of the most potent symbols in theoretical cosmology. It is a hidden structure of pure creation, a theoretical affirmation that the cosmos might be filled with not just sinks and drains, but also with springs and sources. While we may never point a telescope at a celestial fountain and identify it as a white hole, the concept continues to challenge our understanding of time, entropy, and the very nature of existence, suggesting that the mechanisms of creation might be as fundamental to the cosmic architecture as the mechanisms of destruction. While we have explored how extra dimensions, cosmic strings, and vast cosmic webs might form the hidden scaffolding of reality, one of the most provocative theories suggests the ultimate hidden structure is not out there in the cosmos at all, but resides within our own mind. This is the von Neumann-Wigner interpretation, a daring and deeply philosophical take on the mysteries of quantum mechanics. To appreciate its radical proposal, we first need to revisit the infamous measurement problem that lies at the heart of quantum theory. In the bizarre world of the very small, particles like electrons don't exist in a single, definite location until we measure them. Instead, they are described by a wave function, a mathematical expression that encapsulates all the possible states the particle could be in, a blur of probability often called a superposition. The electron is, in a sense, everywhere it could possibly be at once. The great puzzle is what happens during the act of measurement. How does this cloud of possibilities, this spread-out wave of potential, suddenly snap into a single, concrete reality? The moment we look at it, the electron appears in one specific place, as if our very act of noticing it forced it to make a choice. The conventional Copenhagen interpretation, which has long been the textbook explanation, states that the wave function collapses due to the interaction with a macroscopic measuring device. But this has always left a troubling chain of ambiguity. Does the collapse happen when a Geiger counter clicks, when a photographic plate is exposed? Or is it only when the information from that device finally enters the consciousness of a human observer? The physicists John von Neumann and Eugene Wigner followed this logic to its most startling conclusion. They argued that if every physical object, from an atom to a measuring apparatus, is itself just a collection of quantum particles, then nothing made of ordinary matter can truly cause a collapse, because it too would simply become entangled in the superposition. A measuring device pointed at an electron in two places would itself enter a fuzzy state of having recorded two different outcomes. The only thing that seems to break this chain, the only element in the universe that appears to experience a single, definite reality, is consciousness itself. Von Neumann and Wigner proposed that it is the non-physical act of conscious awareness that finally collapses the wave function, transforming possibility into actuality. This interpretation places the human mind, or indeed any form of sentient awareness, at the very center of physical reality. It suggests that consciousness is not a passive byproduct of a mechanical universe, but an active participant in its creation. Without a conscious observer to crystallize it, the world would remain in a ghostly state of potential, a realm of infinite possibilities where nothing is truly real. This idea resonates with certain philosophical traditions like idealism, which have long argued that reality is fundamentally mental. it also leads to some truly mind-bending thought experiments. Imagine a sealed laboratory where a scientist is about to perform a quantum experiment, say, measuring the spin of an atom. From the perspective of another scientist outside the lab, until they open the door and speak to their colleague, the entire laboratory, the equipment, the first scientist, and even the scientist's brain exists in a massive superposition of having seen both possible outcomes. The moment a conscious exchange occurs, a wave of reality sweeps through the system, collapsing not just the atom's state, but the entire history leading up to that conversation. Of course, this interpretation is highly controversial and sits on the fringes of mainstream physics. Critics are quick to point out its major flaws. For one, it seems to reverse the arrow of causation we understand from biology, suggesting that consciousness, which we generally believe emerges from complex physical brains, is somehow a primary force that acts upon the physical world. This leads to the question of what exactly qualifies as a conscious observer. Does a cat have the necessary consciousness to collapse a wave function? What about a worm or a single-celled organism? The theory offers no clear boundary, creating a slippery slope often mocked as the "shut up and calculate" objection, where physics becomes hopelessly entangled with vague philosophy. Furthermore, it makes our universe seem bizarrely anthropocentric, as if the entire cosmos waited in a haze of potential for billions of years until the first conscious life forms evolved to give it definitive shape. Despite these powerful objections, the von Neumann-Wigner interpretation continues to fascinate because it tackles the measurement problem head-on without resorting to an infinite number of branching worlds or other complex metaphysical structures. It offers a singular, if extraordinary, solution that places subjective experience at the foundation of the cosmos. It challenges the materialistic assumption that mind is merely an emergent property of matter, daring to suggest instead that matter may be an emergent property of mind. While few physicists today would bet their careers on this idea, its enduring appeal lies in the profound questions it forces us to confront about our own role in the universe. Are we merely accidental spectators on a pre-existing stage, or are we, in some small but essential way, the very architects of the reality we perceive? Our consciousness, the hidden structure that gives the quantum world its final, definite form. But what if the universe's most fundamental hidden structure isn't made of strings, brains, or quantum loops, but of ones and zeros? What if the entire cosmos, from the farthest galaxy to the very thoughts in your head, is not a fundamental reality, but an immensely sophisticated simulation? A grand virtual reality running on the computer of a civilization so advanced they might as well be gods to us. This is the simulation hypothesis, a concept that has leapt from science fiction into serious philosophical debate, largely thanks to philosopher Nick Bostrom. His formulation presents a sobering trilemma, a set of three possibilities, at least one of which he argues must be true. The first is that almost all civilizations at our level of technological development go extinct before they achieve the capability to create realistic simulations. The second is that any advanced civilization that does reach that stage has absolutely zero interest in running such simulations, perhaps for ethical or philosophical reasons. And the third possibility is that we are almost certainly living in a simulation right now. The logic unfolds with a compelling, almost inescapable rhythm. If we assume that consciousness can, in principle, be simulated, that a sufficiently complex computation could replicate the rich inner world of experience, then a technologically mature civilization could create vast numbers of simulated universes, populated by simulated beings with their own histories and cultures. The number of these simulated minds would, over cosmic time, utterly dwarf the number of original, base reality minds. Therefore, if such simulations are possible and are ever run, the statistical probability that any randomly selected conscious being, like you or me, is living in a simulation is astronomically high. We are far more likely to be one of the countless simulated beings than one of the rare original ones. This isn't proof, but it's a powerful probabilistic argument that forces us to confront the notion that our perceived reality might be a fabricated construct. If this is true, then the ultimate hidden structure of our universe is its source code. The laws of physics we've worked so hard to uncover would not be fundamental laws of nature, but the programmed rules of the simulation, the algorithms that govern the rendering of our reality. This perspective instantly reframes some of the deepest puzzles in physics. For instance, why does our universe appear to be quantized? Why is there a smallest possible unit of space, the Planck length, and a smallest possible unit of time, the Planck time? In a simulation, this makes perfect sense. It's the native resolution of the system. Just as a digital image becomes pixelated when you zoom in too far, space-time itself might reveal its discrete, computational nature at the very smallest scales. The famous double-slit experiment in quantum mechanics, where a particle seems to behave as a wave of possibilities until it is measured, could be seen as a profound optimization technique. The simulation doesn't need to render the definite path of every single particle until that information is required by an observer, saving an unimaginable amount of processing power. The bizarre phenomenon of quantum entanglement, where particles instantly influence each other across vast distances, could be a clever programming shortcut, a kind of local variable linking that doesn't require slower-than-light communication to update. The hunt for potential glitches in the matrix then becomes a serious, if fringe, scientific pursuit. Physicists have pondered whether we might find evidence of the simulation's underlying code. Perhaps the constants of nature, like the speed of light or the strength of gravity, are not arbitrary but are finely tuned values that ensure the simulation runs stably and efficiently, avoiding crashes or paradoxical loops. Some have even suggested looking for signatures of numerical rounding errors in high-energy physics experiments or for odd, repeating patterns in the cosmic microwave background that might hint at the finite memory or processing cycles of the cosmic computer. The very fact that our universe seems to be mathematically describable could be the ultimate clue. We are reverse engineering the programming language in which our reality is written. Of course, this idea is as unsettling as it is fascinating. It leads to a hall of mirrors for our sense of self and purpose. If we are in a simulation, are our lives, our struggles, and our loves any less meaningful? Or does it imbue our existence with a different kind of significance as part of a grand cosmic narrative or experiment? The simulation hypothesis doesn't provide easy answers, but it powerfully expands the scope of what the universe's hidden architecture might be. It suggests that the final layer, the ultimate foundation of everything, may not be a law of physics but a line of code, and that we are living characters in the most immersive story ever told. But if the cyclical universe and the simulation hypothesis stretch our imagination, the next theory we encounter might be the most elegant and profound of all, proposing that the universe's cycles are not driven by violent collisions or quantum bounces, but by a serene, geometric transformation that erases the very concepts of scale and time. This is Roger Penrose's conformal cyclic cosmology, a theory that suggests the entire history of our cosmos, from the Big Bang to its ultimate demise, is just one chapter in an endless sequence of universal epochs which Penrose calls eons. What's truly revolutionary is the mechanism that connects them. In the Big Bounce model, a collapsing universe rebounds into a new expansion. But in Penrose's vision, there is no collapse and no rebound. Instead, the distant, cold future of one eon becomes, through a mathematical sleight of hand, the hot, dense beginning of the next. The key to this incredible transformation lies in the nature of the universe's final state and a concept known as conformal rescaling. In tens of billions of years, our universe's accelerated expansion will lead to a bleak and empty future. all stars will have burned out, black holes will have evaporated through Hawking radiation, and even the protons that make up all matter will have decayed. What remains is a vast, cold, and nearly empty cosmos, populated only by an incredibly dilute sea of massless particles and radiation, essentially, photons and gravitons wandering through an ever-expanding void. In this state, something remarkable happens from a geometric perspective. Because there are no massive particles left, there are no clocks and no rulers. Mass gives a sense of scale. It defines intervals of space and time. Without it, the concepts of distance and duration lose their meaning. The universe becomes effectively timeless and scaleless. Penrose realized that the geometry of this distant future, this barren, infinite expanse, can be mathematically rescaled or conformally transformed to match the geometry of a hot, dense, and incredibly small Big Bang singularity. Through this rescaling, the infinite future of one eon is geometrically identical to the zero-time beginning of the next. The end literally becomes the beginning, not through a violent physical event, but through a smooth, continuous transition in the conformal structure of spacetime. It's as if you had a map of the entire ocean, and by carefully and smoothly shrinking its scale, you could transform it into a map of a single, tiny droplet of water, with the two maps being geometrically indistinguishable. This theory posits a hidden structure that is purely geometric and informational, a conformal bridge that seamlessly links the death of one universe to the birth of its successor. All the information from the previous eon isn't lost, it's effectively reset. The complex structures, the galaxies, the planets, the life are erased, but their fundamental energy and quantum information are carried over, reprocessed through this conformal transformation to provide the initial quantum fluctuations for the next cosmic cycle. This creates an endless chain of eons, each with its own unique history, all connected by this elegant, hidden geometric principle. Unlike other cyclic models, there is no contraction, no crunch, and no bounds. The universe simply expands forever, its useful energy dissipating until its geometry allows it to be seamlessly reinterpreted as the explosive start of something entirely new. Now, such a grand and beautiful theory would remain pure mathematics if not for a startling, testable prediction. Penrose and his collaborators claim to have found the fossilized evidence of a previous eon imprinted on the oldest map we have, the cosmic microwave background. These proposed features are known as Hawking points. Recall that in the far future of any eon, all supermassive black holes will eventually evaporate. In their final moments, they release a tremendous burst of Hawking radiation. According to conformal cyclic cosmology, this energetic outburst from the previous eon, when mapped through the conformal rescaling into the beginning of our own eon, would appear as a source of intense, low-entropy energy. This energy would create a distinct circular pattern of temperature variations in the CMB, a faint, concentric ring, slightly warmer or cooler than its surroundings. These are the Hawking points, theorized to be the ghostly imprints of the last breaths of giant black holes that lived and died in a universe that existed before our own. The search for these points is, of course, a subject of intense debate. Penrose and his team have analyzed data from the Planck satellite and claim to have identified dozens of these anomalous circular patterns in the CMB sky, rings that are much larger and more pronounced than what standard inflationary cosmology would predict. They argue that these features are precisely what you would expect from the conformal mapping of colossal black hole evaporations. The mainstream cosmology community, however, remains largely skeptical. Critics argue that the statistical methods used to find these points may be finding patterns that are simply random fluctuations in the cosmic microwave background, the kind of statistical ghosts that inevitably appear when you search a rich dataset for specific shapes. They point out that the standard inflationary model does an excellent job of explaining nearly all other features of the CMB without requiring any prior universes. The debate hinges on whether these circles are truly anomalous signatures of a pre-Big Bang cosmology or just cosmic pareidolia, the tendency to see meaningful patterns in random noise. For now, the existence of Hawking points is not confirmed, but the very possibility that we could look at the afterglow of creation and see the remnants of a previous cosmos is a breathtaking testament to the power of this theory. It suggests that the universe's grandest hidden structure is a timeless, cyclical geometry, a cosmic Ouroboros where each universe contains within its final, silent moments the seed for its own glorious rebirth. Now, let's turn our attention to a concept so strange that it challenges the very way we classify matter and energy. This is the world of unparticle physics, a speculative but fascinating theory that posits the existence of an entirely hidden sector of reality, one that doesn't play by the familiar rules of mass and energy we take for granted. This idea was first proposed by the esteemed physicist Howard Georgi, and it suggests that our universe might contain a secret, shadow world made of what he termed unparticles. To grasp what this means, think about the fundamental particles we know: electrons, quarks, photons. Each one has a specific mass and fits neatly into our standard model's classification system. But unparticles would be nothing like that. They wouldn't have a definite mass at all. Instead, they would exhibit scale invariance, meaning they would look the same and behave the same way regardless of the energy scale at which you observe them. It's as if you had a substance that, whether you looked at it through a microscope or a telescope, presented the same fuzzy, undefined properties. This is a radical departure from everything we know, suggesting a form of matter that is intrinsically fuzzy, without a single, well-defined identity. The behavior of this unparticled stuff would be bizarre in the extreme. Normal particles, when produced in a collision, carry away specific amounts of energy and momentum in discrete lumps. But unparticles would not. Because they lack a definite mass, they would behave more like a continuous fractional entity. If you were to try and measure the behavior of an unparticle in an experiment, it wouldn't appear as a sharp, distinct particle track. Instead, its signature would be a continuous spectrum of possibilities, almost as if you were seeing a ghostly echo of a particle rather than the particle itself. A helpful, though imperfect, analogy is to think of the difference between water in its different phases. A single ice cube is a discrete, solid object with a definite form. That's like a standard particle. Now imagine a cloud of steam. It has no definite boundary, no single shape. It's a diffuse, continuous presence whose properties are spread out. Unparticles would be like that cloud, a fundamental, ethereal substance that refuses to be pinned down to a single, particulate identity. This strange behavior arises because the unparticle sector is theorized to be a collection of fields that are scale invariant, a property normally associated with pure energy or light, but here applied to a whole new form of tangible yet utterly elusive stuff. So, how would this hidden sector interact with our own familiar world of atoms and forces? The theory proposes that unparticles would couple to our standard model particles only very feebly, through extremely weak interactions, most likely mediated by gravity or via very high energy processes. This makes them incredibly difficult to detect, as they would mostly pass through our detectors and even the entire Earth without leaving a trace. However, their ghostly presence could still make itself known in subtle ways. One of the most exciting possibilities is that unparticles could constitute a portion of the universe's dark matter. Their weak interactions and lack of definite mass make them a compelling candidate for that mysterious, invisible substance that holds galaxies together. Unlike traditional dark matter candidates like WIMP, which are still particulate in nature, unparticled dark matter would be a truly continuous and non-particulate medium, a hidden ocean of scale-invariant stuff permeating the cosmos and providing the gravitational scaffolding for everything we see. Beyond explaining dark matter, unparticle physics could also leave its fingerprint in the most energetic events in the universe. In the extreme environments around colliding black holes or in the hearts of exploding stars, the conditions might be just right for unparticles to be produced or to influence the behavior of known particles in detectable ways. For instance, they could cause subtle deviations in the way energy is distributed in particle collisions at powerful accelerators like the Large Hadron Collider. Scientists actively scour this data for anomalies that don't fit the predictions of the Standard Model, and a signature of unparticles would be a continuous, smooth distribution of missing energy, a telltale sign that something invisible and non-particulate was carrying energy away from the collision. They could also affect the precise properties of other particles, potentially altering the rate at which rare particle decays occur or influencing the delicate balance of forces in ways that we could, in principle, measure with sufficiently sensitive experiments. The implications of discovering unparticles would be nothing short of revolutionary. It would mean that our universe is built not just from the discrete, quantized particles of the Standard Model, but also from an entirely different kind of substance, a continuous, scale-invariant reality operating in the shadows. This would force a profound rewrite of our fundamental textbooks, challenging the very definition of what matter is. It would reveal a deeper layer of complexity in the cosmos, a hidden sector that has been evading our notice simply because it obeys a completely different set of rules. The quest to find evidence for unparticles is a testament to the creativity and daring of modern physics, a search for the ultimate hidden stuff that might not be made of things at all, but of a strange, fractional, and continuous presence that has been intertwined with our reality since the very beginning. Now, let's explore an idea that offers a completely different vision for the origin of mass in the universe. For decades, the discovery of the Higgs boson at the Large Hadron Collider was celebrated as the final, triumphant confirmation of the Standard Model of particle physics. It appeared to solve the puzzle of how fundamental particles get their mass through what's known as the Higgs mechanism, a process where particles wade through an all-pervading Higgs field, gaining mass like a celebrity moving through an adoring crowd. But what if this celebrated story isn't the final word? What if there's a far more dynamic and powerful process at work behind the scenes? This brings us to Technicolor theory, a radical and elegant alternative that suggests the Higgs boson might not be a fundamental particle at all, but a composite object, a mere signpost pointing toward a vast, hidden world of previously unknown forces and particles. The central ambition of Technicolor is to solve the same problem as the Higgs mechanism, explaining how the electromagnetic force and the weak nuclear force, which are unified at high energies, break apart at lower energies to give us the distinct forces we observe today. This process, known as electroweak symmetry breaking, is what endows particles like electrons and quarks with mass. In the Standard Model, this is accomplished by the Higgs field. But Technicolor proposes something much more powerful and aesthetically pleasing. Instead of introducing a fundamental scalar field, the Higgs field, as a separate, added ingredient, Technicolor suggests that the breaking of electroweak symmetry emerges dynamically from a new, incredibly strong force. This force is not gravity or electromagnetism. It's a new kind of interaction analogous to the strong nuclear force that binds quarks together inside protons and neutrons. This hypothetical new force is called the Technicolor force. To understand how this works, imagine the world of the strong force. The strong force operates between quarks, and it's mediated by particles called gluons. One of the most remarkable features of this force is something known as chiral symmetry breaking. At the high energies present in the early universe, quarks are essentially massless and behave symmetrically. But as the universe cools, the strong force between them becomes so powerful that it spontaneously breaks this symmetry. It's as if a perfectly symmetrical, spinning top suddenly wobbles and picks a specific direction to fall. This process doesn't just happen, it's driven by the intense interactions of the quarks and gluons themselves. In doing so, it gives the quarks their effective masses and binds them together to form the protons and neutrons that make up our world. Technicolor theory proposes that a nearly identical process is responsible for giving mass to all fundamental particles. A whole new set of particles, called technoquarks, feel a new technicolor force mediated by particles called technogluons. Just as the strong force binds quarks into protons and pions, the technicolor force binds technoquarks into composite particles. And it is the spontaneous breaking of symmetry in this hidden technisector that dynamically generates the masses for the W and Z bosons, the carriers of the weak force, and, by extension, for all the other particles in the Standard Model. This leads to the most profound implication of the theory, the Higgs boson itself. In the Technicolor framework, the particle we've discovered at the LHC is not the simple, elementary Higgs boson of the Standard Model. Instead, it is what physicists call a composite particle. It's not fundamental, but is actually made up of a technoquark and a technantiquark bound together by the technicolor force, similar to how a meson in the strong force is made of a quark and an antiquark. In this view, the Higgs is more like a technipion, a single light manifestation of a much richer and more complex hidden structure. This completely changes its significance. Finding the Higgs wasn't the end of the story, it was the first glimpse of an entirely new world. This hidden technisector would be a whole new layer of reality, operating under its own set of powerful forces and populated by a host of new composite particles, techni-mesons, techni-baryons, and techni-rhos, all completely invisible to us under normal conditions because they don't interact via electromagnetism. It would be a shadow universe of particle physics, operating according to rules that are both familiar in their structure and entirely new in their application, providing the hidden scaffolding that gives our familiar world its substance and form. The appeal of Technicolor lies in its naturalness and its power to solve some of the aesthetic problems of the Standard Model. The Higgs mechanism, while successful, can feel like an ad hoc addition. The Higgs field is simply put into the equations by hand to do its job. Technicolor, by contrast, generates mass through a known dynamical mechanism, a process we already observe happening with the strong force. It replaces a mysterious, fundamental field with a powerful, familiar interaction. Furthermore, the elementary Higgs boson of the Standard Model has a perplexing problem. Its mass seems unnaturally tuned. Quantum corrections should drive its mass up to an enormous scale, far beyond what we observe, unless some incredible fine-tuning or miraculous cancellation occurs. This is known as the hierarchy problem. In Technicolor, this problem simply evaporates. Because the Higgs is a composite particle, its mass is protected. It has a finite size, and this size acts as a natural cutoff for those troublesome quantum corrections, stabilizing its mass at the scale we observe without any need for fine-tuning. It's a more robust and self-consistent explanation from a theoretical standpoint. Despite its elegance, the original formulations of Technicolor faced significant challenges, primarily from precision measurements of the electroweak force. The theory predicted subtle deviations from the Standard Model that were not initially observed in experiments. However, the story didn't end there. Just as theories evolve, so has Technicolor. Modern incarnations, often called walking Technicolor, have refined the idea. In these updated models, the Technicolor force walks, meaning it evolves very slowly with energy scale. This walking behavior can suppress those problematic deviations, bringing the theory's predictions back into alignment with existing data, while still predicting a rich spectrum of new, heavy composite particles that could be within the reach of a future, more powerful collider. The search for this hidden sector is now one of the great quests for the next generation of particle physicists. They will be looking not just for one particle, but for an entire technihadron spectrum, a whole new periodic table of composite objects born from the Technicolor force. Discovering even one of these would be like finding a single, strange seashell on the beach, and realizing it points to an entire, undiscovered continent just beyond the horizon. A continent whose powerful, hidden dynamics are responsible for building the very fabric of our material world. After contemplating how our entire cosmos might be a simulation or one cycle in an endless conformal sequence, we arrive at a theory that offers perhaps the most visceral and geometric nesting of realities imaginable. This is the black hole universe hypothesis, a staggering concept proposing that the universe we inhabit is not the top level of existence, but is instead the interior of a colossal black hole residing within a much larger parent universe. In this view, the Big Bang was not a singular, standalone event, but the violent birth of a new space-time continuum from the gravitational collapse of a massive object in another reality. The connection between black holes and new universes hinges on a remarkable similarity. When we describe the Big Bang, we speak of a state of near-infinite density and temperature, a point from which all space and time began to expand. Now consider the final fate of a massive star collapsing into a black hole. From the perspective of an outside observer in the parent universe, matter falling toward the event horizon appears to slow down and fade from view due to extreme gravitational time dilation. But from the perspective of the matter itself crossing the event horizon, the journey continues inward toward the center, the singularity. In the standard classical picture, this singularity is a point of infinite density where the laws of physics break down. However, when we incorporate quantum mechanics, this picture may change dramatically. Some theories suggest that at the very final moment of collapse, just before the singularity would form, quantum gravitational effects could generate an immense repulsive force. This force would not simply halt the collapse, but would rebound it, triggering a rapid, explosive expansion of the region inside the black hole's event horizon. This internal rebound would look from the inside exactly like a Big Bang. The event horizon of the parent black hole becomes the cosmic horizon of the newborn universe, the point beyond which no signal can ever reach us, not because of an edge, but because space is expanding faster than light can travel across it. We are not living on the outside of a sphere looking out. We are living on the inside of a black hole's boundary, with all of our cosmic space contained within it. This leads to a mind-bending vision of a fractal multiverse, an infinite regress of cosmic nesting. If our universe exists inside a black hole, then every black hole that forms within our cosmos, every stellar remnant, every supermassive giant at the heart of a galaxy, could itself be the seed for an entirely new universe completely disconnected from our own. When a star collapses in our night sky, it may not be creating a terminal endpoint, but a new beginning, birthing a full-fledged cosmos in a realm we can never access. Our entire universe, with its hundreds of billions of galaxies, could be just one such bubble within a vaster meta-universe, and that parent universe, in turn, could be one of countless others inside an even grander structure, creating a Russian doll-like cascade of realities, each with its own unique history and physical laws. This provides a powerful and elegant mechanism for a prolific multiverse, one driven not by abstract quantum branching or inflationary fields, but by the fundamental astrophysical process of gravitational collapse. One of the most profound implications of this hypothesis is a potential explanation for why our universe appears so finely tuned for life. The specific laws of physics we observe, the strength of gravity, the mass of the electron, the number of spatial dimensions might not be fundamental, immutable truths. Instead, they could be inherited properties passed down from the parent black hole that gave birth to us. The formation of a black hole is determined by the physical constants of its host universe. When it collapses and rebounds into a new cosmos, those initial conditions could be imprinted upon the new universe's fundamental parameters. In this cosmic Darwinism, the laws of physics in any given universe are not random, they are a product of their ancestry. Universes that give rise to many black holes are, by definition, prolific, spawning many descendant universes. If the ability to form black holes is linked to having certain physical constants that also, coincidentally, allow for the formation of stars, planets, and complex chemistry, then it is no surprise that we find ourselves in such a universe. We live in a cosmos whose rules are conducive to black hole formation because we are the offspring of a black hole from a universe that also had life-friendly rules. This elegantly sidesteps the need for a singular, miraculous fine-tuning, suggesting instead a form of cosmological natural selection, where the multiverse is populated by universes that are good at making more universes, and we are simply along for the ride within one of these fertile cosmic lineages. But for all the grandeur of these ideas, from cosmic strings to colliding brains, we've been operating under a quiet, profound assumption that the stage of spacetime itself is smooth, featureless, and plays no favorites. This principle is known as Lorentz invariance, a cornerstone of Einstein's relativity that ensures the laws of physics are the same for all observers, no matter their speed or direction. It's the reason the speed of light in a vacuum is the ultimate cosmic speed limit, a constant that underpins the very structure of reality. But what if this cherished symmetry is not perfect? What if, at the very highest energies or the smallest possible scales, this foundational pillar of physics shows tiny, telling cracks? This brings us to Theory 26, Lorentz violation, a class of ideas suggesting that spacetime itself might possess a hidden grain, a subtle directionality that breaks the universal symmetry and reveals a hidden, preferred frame of reference in the cosmos. The concept of Lorentz violation is one of the most radical and subtle challenges to modern physics. It proposes that the vacuum of empty space is not a perfectly uniform and isotropic backdrop. Instead, it might have a built-in directionality, much like the grain in a piece of wood. In such a universe, the speed of light might not be exactly the same in all directions. A photon traveling north, for instance, might move infinitesimally faster or slower than a photon traveling east. Furthermore, different types of particles could experience this vacuum in different ways, meaning that high-energy protons and electrons might not share the exact same ultimate speed limit. This isn't just a minor adjustment. It would mean that there is a hidden compass for the universe, a secret preferred frame, against which all motion could, in principle, be measured, overturning a century of relativistic thinking. The reason we don't notice this in our daily lives is that the effect is theorized to be vanishingly small, only becoming significant at energies approaching the Planck scale or for particles traveling across billions of light years. It's a hidden anisotropy woven into the fabric of reality itself, a ghostly signature of a deeper, more fundamental structure. Where could such a fundamental grain come from? Many of the leading theories of quantum gravity provide a natural habitat for Lorentz violation. In loop quantum gravity, for instance, the spin network that constitutes space is a discrete, granular structure. While it appears smooth on large scales, a particle traveling across it at near light speeds might feel this underlying granularity. Much like a car driving at high speed on a perfectly smooth road, might still transmit the tiniest vibrations from the asphalt's texture. In some models, this could cause subtle differences in propagation speed depending on the particle's energy or its direction relative to the spin network's hidden geometry. Similarly, in theories involving a spacetime foam, a concept dating back to John Wheeler, the vacuum is theorized to be a seething, chaotic froth of virtual black holes and wormholes at the Planck scale. A particle traversing this turbulent quantum landscape would not have a perfectly smooth journey. Its path would be slightly jostled, and these minuscule interactions could add up over cosmic distances, potentially causing higher energy photons to travel at a very slightly different speed than their lower energy counterparts. In this view, the constancy of light isn't a fundamental law, but an emergent property that holds very well at our low energies, but begins to fray at the extreme frontiers, revealing the foamy, turbulent nature of the quantum vacuum. The hunt for this cosmic grain is one of the most exacting endeavors in all of science, pushing the limits of our precision measurement capabilities. Physicists are essentially trying to detect a deviation in the 16th decimal place, searching for the faintest whisper of a broken symmetry. They conduct these searches in several ingenious ways. One method is to look for energy-dependent dispersion in light from the most violent and distant astrophysical sources, such as gamma-ray bursts or active galactic nuclei. If higher energy gamma-ray photons interact with a grainy spacetime differently than lower energy ones, they should arrive at our telescopes at slightly different times after their multi-billion-year journey. By analyzing the arrival times of these photons with incredible precision, scientists can set stringent limits on any Lorentz-violating effects. Another class of experiments searches for directional dependence, using the Earth itself as a rotating laboratory. Exquisitely sensitive optical or microwave resonators are monitored as our planet spins on its axis and orbits the Sun. If the speed of light were different along one axis in space, the resonant frequency of these cavities would undergo a tiny, periodic shift as their orientation changes relative to this hidden cosmic frame. These experiments have become so precise that they can detect shifts equivalent to a change smaller than the diameter of a single proton in the distance between the Earth and the Sun. The implications of actually discovering a Lorentz violation would be nothing short of revolutionary. It would be the ultimate clue that we are on the verge of a new understanding of reality, providing direct experimental evidence for a quantum nature of gravity. A confirmed violation would immediately rule out entire classes of theories and provide crucial guidance for building the final theory. It would tell us that spacetime is not a smooth, continuous stage, but has a hidden texture, a grain, a foam, a spin network that becomes visible only at the most extreme energies. It would mean that the vacuum is a physical medium with properties, a new ether for the 21st century, though one completely different from the mechanical ether of the 19th. Finding this hidden cosmic compass would not break physics. It would illuminate its next great frontier, proving that the deepest secrets of the universe are encoded not just in the particles and forces, but in the subtle, directional whispers of spacetime itself. But if the idea of a grainy spacetime challenges our classical intuition, the next theory we encounter may be the most profound of all, suggesting that space and time themselves are not fundamental ingredients of reality, but rather illusions that emerge from something far more basic. This is the theory of emergent spacetime, a revolutionary perspective that turns our understanding of the cosmos inside out. For centuries, we have treated space and time as the ultimate stage, the immutable container within which the drama of the universe unfolds. Einstein wove them together into a single, dynamic fabric called spacetime, but he still treated this fabric as the foundational layer. Emergent spacetime theory proposes something far more radical, that this fabric isn't fundamental at all. It suggests that what we perceive as space and time are collective phenomena that arise from the interactions of countless tiny, non-spatiotemporal building blocks, much like the smooth flow of a liquid emerges from the chaotic jostling of trillions of individual molecules. To grasp this counterintuitive idea, consider some powerful analogies from our everyday world. Take temperature. When you feel that a cup of coffee is hot, you're not measuring a fundamental property of a single substance. The hotness doesn't exist at the level of individual water molecules. A single molecule doesn't have a temperature, it only has kinetic energy, a speed. Temperature is an emergent property, a statistical average of the frenetic motion of countless molecules. Only when you have a vast ensemble of these particles does the concept of temperature even make sense. Similarly, think about the smooth, continuous flow of water. To a fish swimming in a stream, water appears as a continuous, fluid medium. It doesn't perceive the individual H2O molecules, it experiences the collective behavior of them all. The laws of fluid dynamics describing waves, vortices, and pressure are emergent laws. They are excellent approximations that work on human scales, but they break down completely if you try to apply them to a single molecule. In the same way, emergent spacetime theory suggests that the smooth, continuous geometry described by Einstein's equations is an emergent approximation. It works perfectly for describing the orbits of planets and the bending of starlight, but it must break down at the tiniest possible scales, giving way to a hidden realm of entities that are not themselves living in space or time as we know them. So, if spacetime is emergent, what is it emerging from? The leading candidates in modern physics point toward information and quantum entanglement. In this view, the fundamental building blocks of reality are not tiny vibrating strings or grains of space, but quantum bits of information qubits. These are the most basic units of quantum information, and theorists propose that the cosmos at its most fundamental level is a vast, evolving quantum state, a cosmic quantum computer. In this picture, space is not a pre-existing container. It is a way of encoding relationships between these qubits. Two qubits that are highly entangled with each other are interpreted as being close together in space, while qubits with weak entanglement are far apart. Distance in this emerging view is not a fundamental measure but a measure of quantum connection. The three-dimensional space we move through and the relentless flow of time we experience are both believed to arise from the complex web of entanglement linking these fundamental informational bits. This provides a stunning new interpretation of the holographic principle we discussed earlier. The two-dimensional surface that encodes our reality isn't just storing information about a separate three-dimensional world, it is the primary reality. The three-dimensional universe, with all its depth and volume, is a grand illusion projected from the intricate information processing happening on that lower dimensional boundary. This perspective is being actively explored in several of the most promising approaches to quantum gravity. In certain formulations of string theory, the smooth spacetime of general relativity is understood to emerge from the interactions of the theory's fundamental objects, just as the properties of a solid emerge from the atomic lattice that constitutes it. In loop quantum gravity, spacetime emerges from the evolving relationships within the spin network. But perhaps the most concrete and accessible example of emergent spacetime comes from a tool used by theoretical physicists called the AD/CFT correspondence. This is a precise mathematical duality, a kind of dictionary, that translates a theory of gravity in a hypothetical anti-de Sitter space, a universe with a negative cosmological constant, into a conformal field theory, which is a quantum theory without gravity that lives on the boundary of that space. The miraculous thing about this correspondence is that it shows how a dimension of space can literally emerge from a quantum system that doesn't have that dimension. The gravitational force and the geometry of the bulk space are entirely encoded in the quantum entanglement patterns of the particles living on the lower dimensional boundary. This isn't just a vague analogy, it's a mathematical proof of principle that spacetime and gravity can be emergent phenomena. The implications of this are as profound as they are disorienting. If spacetime is emergent, then the Big Bang was not the beginning of space and time, but the moment when this emergent structure crystallized into the form we recognize. It suggests that there could be a more fundamental, non-spatiotemporal phase of the universe that preceded what we call the Big Bang, a phase governed by pure quantum information and logic. This could provide a natural resolution to the initial singularity, that point of infinite density where our current laws of physics break down. There was no singularity because there was no point in a pre-geometric sense. There was only a transition from a disordered, non-spatial state to an ordered, spatial one. Furthermore, this view elegantly explains the deep connection between gravity and thermodynamics, the science of heat and disorder. We've long known that black holes have entropy and temperature, properties normally associated with complex systems with many microscopic parts. If spacetime itself is emergent from a vast number of quantum constituents, then it makes perfect sense that it would obey thermodynamic principles. Gravity, in this emergent view, might not be a fundamental force at all, but rather an entropic force, a side effect of the system's natural tendency to maximize its disorder, much like the way a stretched rubber band snaps back to a more disordered, higher entropy state. Embracing the idea of emergent space-time forces us to reconsider the very nature of reality. It suggests that the universe is not a collection of objects in space and time, but a network of relationships from which space and time are derived. The solidity of the chair you're sitting on and the vast distances between galaxies are both magnificent illusions, incredibly persistent and consistent patterns arising from an underlying quantum reality that is utterly alien to our everyday experience. The quest to uncover this deepest of all hidden structures is not just about finding a theory of quantum gravity. It is about answering the most basic question of all: what is the world ultimately made of? And the answer seems to be pointing away from stuff and forces and towards something more abstract and powerful: information, connection, and the intricate computation from which the stage of reality itself is continuously being built. And so we arrive at a hidden structure of a completely different kind, one not woven from space-time or dark matter, but from probability and biology. This is the puzzle known as the Fermi paradox and the terrifying concept it spawned, the Great Filter. After exploring the universe's physical architecture, we now turn to its potential inhabitants, or rather, the startling silence that suggests there might be very few of them. The paradox, named for physicist Enrico Fermi, is deceptively simple. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of these stars are billions of years older than our Sun, providing ample time for intelligent civilizations to arise, spread, and colonize entire galaxies. The raw numbers suggest the cosmos should be teeming with life, a bustling interstellar metropolis. Yet when we listen, all we hear is a profound and eerie silence. As Fermi famously quipped during a conversation about extraterrestrial life, "Where is everybody?" This contradiction between the high probability of alien existence and the total lack of evidence for it points toward a hidden barrier, a cosmic bottleneck. This is the Great Filter hypothesis, a concept developed by economist Robin Hanson. It proposes that the process of evolution from non-living chemistry to a durable, space-faring civilization must involve at least one step that is extraordinarily improbable, a barrier so difficult to pass that it effectively filters out almost every candidate. Think of it as a series of gates on the path to interstellar existence. The Great Filter is that one gate, perhaps hidden among the others, that is almost always locked. Its location is the single most important question for the future of humanity. Is this filter behind us a hurdle we have already miraculously cleared? Or is it still ahead of us, waiting in our future as a potential doom that has already silenced every other civilization in the galaxy? If the filter is behind us, it means we are astoundingly rare and precious. We are the cosmic lottery winners. In this scenario, one of the steps we have already passed was far more difficult than it appears. Perhaps the origin of life itself, the transition from a primordial soup to a self-replicating molecule, is the monumental barrier. While the ingredients for life seem common throughout the cosmos, the actual spark that ignites that first, fragile genetic code might be an event of such staggering improbability that it has only happened a handful of times in the entire Milky Way. Another candidate filter behind us could be the leap from simple prokaryotic cells to complex eukaryotic cells. For over 2 billion years, life on Earth was stuck at the single-celled stage. The transformation that allowed for complex multicellular life required a freak symbiotic event, a larger cell engulfing a smaller one, leading to the creation of mitochondria, the powerhouses of complex life. This event might be the true bottleneck, a biological innovation so rare that it makes every animal, plant, and fungus you see a descendant of a 1 in a trillion fluke. If the great filter lies in our past, it means the universe is largely empty and silent, not because civilizations destroy themselves, but because they never even get started. We are, in effect, alone, or at least among the first and only voices in a cosmic darkness that has yet to be filled. The alternative is far more unsettling. If the filter is not behind us but ahead of us, then our apparent rarity is not a sign of our fortune, but a portent of our doom. In this scenario, the development of intelligent, tool-using species might be relatively common. The universe could be littered with the fossilized remains of civilizations that reached a stage similar to our own, only to be wiped out by a predictable and nearly inescapable catastrophe. What could this future filter be? One terrifying possibility is that the development of advanced technology inevitably leads to self-destruction. The discovery of nuclear fission gave us the power to obliterate our civilization in an afternoon, a power that will only grow with future technologies like engineered pandemics or runaway artificial intelligence. It's possible that once a species gains the ability to manipulate the fundamental building blocks of reality, it's only a matter of time before that power is turned inward, either by accident or through deliberate conflict. Another potential filter is what's known as the berserker hypothesis, the idea that the first civilization to arise in any galaxy, fearing competition, might create self-replicating probes designed to seek out and eliminate any emerging intelligent life. In this dark forest of a universe, the silence we hear is the silence of the hunt, and any species naive enough to broadcast its location might soon find itself on the receiving end of a sterilizing impact. This framework transforms the Fermi paradox from a simple curiosity into a profound tool for introspection. The great filter is a hidden structure of probability governing the prevalence of intelligence, and our own fate hinges on where it is located. If we were to discover simple, fossilized bacterial life on Mars or Europa, it would be momentous but also deeply alarming. It would suggest that the first step, the origin of life, is not the great filter. If we were to find the ruins of a complex, long-dead animal civilization on another world, the alarm bells would ring even louder. Each discovery of life that made it partway up the ladder of complexity would make it statistically more likely that the great filter is still ahead of us, waiting. Our continued survival and the silence of the cosmos may be the strongest evidence we have that we are navigating a minefield that has already claimed countless others. This isn't a reason for despair, but for profound caution and wisdom. Understanding the great filter as a hidden structure of existence forces us to recognize the fragility of our moment in cosmic history and the incredible responsibility that comes with the power we now wield. Our greatest task may not be to find other life, but to ensure that we successfully pass through the filter that has silenced every other voice. Now, we venture into a theory that offers a truly unique solution to one of the most persistent riddles in all of science, the quantum measurement problem. Why does the fuzzy, probabilistic world of atoms and electrons give way to the solid, definite reality we experience every day? The theory of quantum Darwinism proposes a fascinating answer, suggesting that the transition from quantum weirdness to classical certainty isn't driven by a conscious observer, but by a hidden process of selection and amplification that works much like natural selection in biology. It posits that our familiar, objective world emerges because the universe itself has a hidden Darwinian structure, constantly favoring and copying the most stable quantum states. To grasp this, let's return to that baffling quantum superposition, where a particle exists in multiple states at once. The traditional Copenhagen interpretation says this cloud of possibilities collapses into one reality only when it is measured, but it never satisfactorily defined what constitutes a measurement. Quantum Darwinism sidesteps this problem entirely by removing the need for a special observer. Instead, it focuses on the relentless interaction between a quantum system and its environment. Think of the environment as everything surrounding a particle: the air molecules, photons of light, stray electromagnetic fields, and even the cosmic microwave background radiation. No quantum system is ever truly isolated. It is constantly being probed, poked, and observed by this chaotic sea of environmental particles. This is where the Darwinian process kicks in. When a quantum system interacts with its environment, it imprints information about its state onto the environment, but not all states are created equal. Some quantum states are fragile and get scrambled beyond recognition by these interactions, much like a delicate species that cannot survive in a harsh ecosystem. Other states, however, are robust or pointer states. These are the quantum equivalent of a hardy species perfectly adapted to its environment. When a robust state interacts with the environment, it doesn't get destroyed. It leaves a clean, distinct, and redundant copy of itself on many different parts of the environment. A single photon bouncing off an object, for instance, carries away information about that object's position. But in reality, countless trillions of photons are constantly doing this, each one independently recording the same information. This process creates what physicists call branching, not into parallel worlds, but into a single, stable classical reality where the information about the system state has been widely disseminated and copied. This redundancy is the cornerstone of quantum Darwinism and the source of our objective reality. For a fact to be considered objective, it must be available to multiple observers who can all agree on it without having to compare notes. In this framework, the environment acts as a passive, unintentional communication channel. When you walk into a room and see a chair in a specific location, you're not causing the chair's position to materialize. You are simply tapping into the vast number of environmental records that have already been created. The air molecules that have bounced off the chair, the photons of light that have reflected from it, they all carry the same redundant message: the chair is here. Your brain, as a measurement device, simply accesses this pre-existing, widely broadcast information. The reason we all agree on the chair's location is not because we share some mystical consciousness, but because we are all independently reading from the same cosmic data bank, which has been filled with countless identical copies of that information. The fragile superpositions die out, unable to leave a lasting imprint, while the robust pointer states are selected for by the environment, bred into existence through countless interactions until they become the unambiguous facts of our classical world. This perspective provides a powerful and elegant way to understand the collapse of the wave function as an objective physical process, not a subjective mystery. The wave function doesn't collapse because someone looks at it. It effectively collapses for all practical purposes because its information has been so widely copied and dispersed into the environment that the original superposition can no longer be accessed. It's lost in the noise, becoming effectively irreversible. This idea connects the quantum realm to the classical world through the universal language of information and selection. It suggests that the solidity of the world around us is not an illusion, but a stable consensus reached through a continuous, unconscious process of environmental fact-checking. The hidden structure of reality, in this view, is a dynamic, information-theoretic ecosystem where only the fittest quantum states survive to become part of our shared experience. And now we bring our cosmic journey all the way home to the very solar system we call our own, where a hidden structure of a different kind may be silently shaping the fringes of our celestial neighborhood. This is the Planet 9 hypothesis, a compelling theory suggesting that a large, undiscovered world, a true new planet, is lurking in the dark, vast expanse beyond Neptune, patiently waiting to be found. The evidence for this elusive giant doesn't come from a direct glimpse through a telescope, but from the subtle, collective whisper of gravitational influence etched into the paths of smaller, distant objects. Out in the frigid darkness, far beyond the orbit of Pluto, lies the Kuiper Belt, a vast disk of icy remnants left over from the solar system's formation. Astronomers studying the orbits of the most distant of these Kuiper Belt objects noticed something profoundly strange. A small group of these objects, with orbits that take them hundreds of times farther from the Sun than Earth, don't just swing around the Sun randomly. Instead, their elongated orbits are mysteriously clustered together, all pointing in roughly the same direction and tilted at a similar angle relative to the plane of the solar system. For this clustering to occur by random chance is statistically akin to throwing a handful of confetti and having it all land in a neat, straight line. The most elegant explanation is that an unseen, massive planet is herding them, its persistent gravitational tug over millions of years shepherding their orbits into this peculiar alignment. The hypothetical properties of this world are as fascinating as the detective work behind its prediction. Planet 9, as it's been nicknamed, is not thought to be a small, rocky body like Earth or a gas giant like Jupiter. Current models suggest it's a mini Neptune or a super-Earth with a mass roughly 5 to 10 times that of our own planet. Its orbit would be equally monumental and strange, a colossal, elliptical path that takes it on a grand tour of the outer solar system. At its closest approach, or perihelion, it might come within 200 to 300 astronomical units of the Sun, which is still several times farther out than Neptune. At its most distant point, or aphelion, it could retreat to a staggering 600 to 1200 astronomical units, drifting in a profound and lonely darkness where the Sun would appear as little more than an exceptionally bright star. A single year on this world, one complete orbit around the Sun, could take anywhere from 10,000 to 20,000 Earth years. This incredibly long orbital period is precisely why it has remained undetected for so long. We have only been systematically mapping the skies for a tiny fraction of its immense celestial year. The search for this phantom planet is one of the great observational challenges of modern astronomy, a painstaking process of hunting for a single, faint, and incredibly slow-moving needle in a cosmic haystack. Astronomers are using some of the world's most powerful telescopes, like the Subaru telescope in Hawaii, to scan vast swaths of the sky. They are not looking for a bright, obvious dot, but for a tiny shift in position against the backdrop of fixed stars over many nights, even years. The difficulty is compounded by the fact that its predicted location is only loosely constrained. It could be almost anywhere along its gigantic, multi-millennial orbit. Furthermore, at such immense distances, it would receive very little sunlight and would therefore be exceptionally dim, reflecting only a faint glimmer that is easily lost in the glare of the Milky Way or masked by closer, faster-moving asteroids. Researchers are also employing sophisticated computer simulations to model the gravitational effects of such a planet, testing whether its presence can not only explain the clustered Kuiper Belt objects, but also other minor solar system anomalies, such as the unusual tilt of the Sun's axis and the orbits of some objects that swing perpendicular to the planetary plane. The potential discovery of Planet 9 would be an event of monumental historical and scientific significance. It would be the first true planet added to our solar system's roster in modern history, a discovery that would rewrite textbooks and captivate the global imagination in a way not seen since the finding of Pluto in 1930. But beyond the sheer excitement, confirming its existence would provide a profound validation of gravitational dynamics as a tool for discovery, echoing the way Neptune itself was found in the 19th century by analyzing perturbations in the orbit of Uranus. It would revolutionize our understanding of the solar system's formation and evolution, suggesting that the early planetary disk was capable of forming and then ejecting such a substantial world into a distant, stable orbit. This hidden architecture in our own backyard serves as a powerful and humbling reminder that even in a cosmos filled with dark matter, hidden dimensions, and parallel universes, there are still fundamental mysteries waiting to be solved right here within the gravitational sway of our own sun. The hunt for Planet 9 is a thrilling testament to the fact that exploration is not over, that the map of our own immediate cosmic territory is still incomplete, and that the next great discovery might be lurking in the darkness just beyond our current vision, patiently waiting for a curious mind to finally bring it into the light. And so our journey across 30 incredible theories about the hidden structures of the cosmos comes to a close. We have ventured from the minuscule, quantum granular weave of space-time to the unimaginable vastness of the multiverse, from the one-dimensional cracks of cosmic strings to the holographic projection of our entire reality. We have pondered universes born from the collapse of stars in a parent cosmos, considered the possibility that our existence is a sophisticated simulation, and even explored the idea that our very consciousness might play a role in crystallizing reality from a sea of quantum potential. This breathtaking spectrum of ideas, from the rigorously mathematical to the wildly speculative, showcases the sheer creative power of the human mind when confronted with the ultimate mysteries. None of these are proven facts. They are the leading edges of our understanding, the most compelling maps we have for territories we have only just begun to explore. They represent humanity's collective and courageous attempt to pull back the curtain, to glimpse the blueprints and scaffolding behind the magnificent spectacle of the universe we inhabit. What is truly remarkable is not that we have settled on a single, definitive answer, but that our quest has revealed such an astonishing diversity of possibilities. The fact that brilliant minds can look at the same cosmos and propose frameworks as different as loop quantum gravities, spin networks, string theories, vibrating strings, and the emergent spacetime from quantum information tells us something profound. It reveals that reality, at its most fundamental level, is far stranger and more wonderful than our everyday experience could ever suggest. We are like detectives in a cosmic mystery, piecing together clues from the faint afterglow of the Big Bang, the strange spin of distant galaxies, and the bizarre behavior of particles in the lab. Each theory is a different hypothesis, a different storyline that tries to make sense of all the evidence. This is not a sign of failure, but a sign of a science that is vibrantly alive, pushing against the very boundaries of what is knowable. This entire endeavor, from the first curious gaze at the stars to the construction of colossal particle colliders, is driven by a deep and innate human need to understand our place in the grand scheme of things. We are not content to simply live in the universe. We are compelled to ask how it works, why it exists, and what its underlying rules might be. Every one of these 30 theories is a testament to that insatiable curiosity, that relentless drive to look beyond the obvious and seek the hidden layers of truth. It is this drive that has taken us from believing the Earth was the center of all creation to understanding that we orbit an average star in a remote corner of a galaxy that is just one among 2 trillion in the observable universe. And now we dare to ask what lies beyond even that, in the realms of higher dimensions, parallel worlds, and cyclical eons. The journey of cosmic discovery is the greatest story ever told, and we are all part of it. Now we turn the conversation over to you. After this tour through the universe's potential hidden architectures, which idea resonated most deeply? Does the elegant simplicity of modified gravity appeal to you, or the mind-bending totality of the mathematical universe hypothesis? Are you captivated by the cyclical renewal of conformal cyclic cosmology, or do you find the practical mystery of dark matter's cosmic web more compelling? Perhaps you have your own favorite theory we explored, or a thought about a hidden structure we have yet to imagine. Share your thoughts and your number 1 pick in the comments below. We are incredibly excited to hear which of these cosmic blueprints captures your imagination. The search for understanding is a shared adventure, and your perspective is a vital part of it. If you enjoyed this deep dive into the fabric of reality, make sure to subscribe and hit the notification bell so you don't miss our next journey to the frontiers of knowledge. Until then, keep looking up and wondering about the incredible, hidden depths of this strange and beautiful universe we call home.